2004. The Cassini space probe approaches the ringed planet Saturn and its 56 moons. It discovers something almost unimaginable, conditions that might support life. And if those conditions could exist so close by, what might we find in the next galaxy? On a planet just like Earth. For millennia, we humans have looked to the skies and wondered whether we're alone in the universe. Today, we're closer than ever to knowing the answer. Some scientists believe we'll get our first look at our extraterrestrial cousins in the near future.
I hope it's in the next 10 years, and I'm ready for it next week, so the sooner the better.
What's more, we could find these aliens not on distant planets in unexplored galaxies, but right next door in our own solar system. Scientists are now honing in on proof that ET is out there and living on the most hazardous of worlds. Our safari will journey to 7 destinations in our solar system to see just where these creatures could be and what they might look like. These exotic lands are unimaginably harsh. Life as we think of it would perish in an instant. But alien life may be far tougher than we expect, as we're learning from a surprising group of living things right here on Earth. Until just a few decades ago, we were sure our planet was unique. It is the only one we've found so far that has nurtured the evolution of millions of species. Thanks to its abundant sunshine, warm water, and protective atmosphere. We logically concluded that life needed each of those things, a conclusion that ruled out all other known worlds in our solar system. But then, biologists began combing some of the Earth's darkest and coldest places. And to their surprise, they found living, breathing creatures. Biologists call these organisms extremophiles. Some don't need light or oxygen. Others survive in tremendous atmospheric pressure. It seems life can turn up practically anywhere. Take Antarctica. After years of searching this arid, frozen landscape, scientists doubted they'd find anything alive. But in 1999, a team of explorers unearthed a rock from 6 feet under the ice. What they found amazed them. When they cracked the rock open, they found it teeming with tiny creatures. Here, at temperatures of 68 degrees below zero and 6 feet under solid ice, life had found a foothold.
Biologists have been increasingly discovering life, not kangaroos, but, simpler forms of life that live at very cold temperatures, very high temperatures, very great pressures, even in places where there's sort of a high degree of radiation. It turns out life is able to live in a much wider variety of environments on our own planet than we used to think.
And if life can survive extreme conditions, not just here at home, but elsewhere in our solar system, think of what this could mean.
Unless there's something extraordinarily miraculous about our solar system or our planet, then life has got to be extremely commonplace. I mean, there's got to be large numbers of worlds with life, and some of them would have cooked up intelligent life.
In the beginning, our Earth was as deadly a planet as any. Over the first billion years of Earth's existence, cosmic debris pummeled it mercilessly. The impacts turned its surface into a broiling, seething inferno where life was impossible. But once the solar system settled down and the Earth began to cool, water appeared, setting the stage for life. In 1953, researcher Stanley Miller proved in a lab experiment just how easily life on Earth got its start. He combined water with hydrogen, methane, and ammonia, components of the Earth's early atmosphere. Then he zapped his solution with an electric charge to simulate lightning. His results shocked the world. Miller had created organic molecules called amino acids, the protein building blocks of all living things. If lightning helped jumpstart life on Earth, could it have done the same on other planets? Galactic probes have now found the ingredients in Miller's experiment throughout our solar system, including one essential to life.
One of the requirements that every form of life that we know about on Earth has, every single one, is liquid water. We've used evidence for liquid water to kind of guide our search for habitable environments.
Our safari is headed to 7 worlds, some possibly rich in water, where scientists believe aliens might be hiding. While any life there might have begun much like life on Earth, how it looks now is anyone's guess. We begin in the world that has always fired our imaginations, the planet right next door, Mars. Of all the planets where we've looked for life, it's the one we've studied most. The scientist who may get the first look at Martians, if they're found, is Steve Squires, principal investigator for NASA's Mars rovers.
Mars has always had, among all the planets, I think, a special fascination for humans. For a very long time, we've known enough about Mars to know that it is probably the most Earth-like.
It may be the most like Earth, with an atmosphere and seasons, but we humans would perish quickly on Mars. Its air is thin, 40 times thinner than the air at the top of Mount Everest. And it sits in a bad neighborhood of our solar system, near an asteroid belt. Its atmosphere is too flimsy to protect it. Asteroids continually bombard its surface. Violent winds can whip Mars's sandy soil into storms that consume the entire planet for weeks and spawn tornadoes 8 kilometers high. Midday temperatures at the equator of 1 degree Celsius fall to -70 at night. David Grinspoon is a curator of astrobiology at the Denver Museum of Nature and Science. As he sees it, Mars would be warmer if it wasn't a planetary runt.
When I grab coffee on a cold morning, I know that a small espresso is going to cool off quickly, whereas a larger coffee is going to stay warm much longer. Large objects stay warm longer because their interiors are shielded from the outside where the cooling occurs. And planets are exactly the same way. A small planet will cool off early in its history. A larger planet like Earth will stay warm for billions of years, which makes it a better place probably to look for life.
Despite Mars's drawbacks, it has always fascinated scientists because its terrain seemed to give evidence that it might support life. Its dynamic landscape of mountains, volcanoes, and deep ravines is not unlike our Earth. To early astronomers, these features look like oceans and rivers, and even a system of canals, supposedly not just supporting life, but actually produced by it.
Percival Lowell in the United States observed these things and inferred that, in fact, these things were so straight and so regular in geometry that they had to have been the product of intelligent life. Okay? Well, he was right. The problem was the life was at the wrong end of the telescope. In viewing this thing visually through a telescope eyepiece, the human eye-brain combination started to connect things that weren't really there.
Lowell was not alone. Some scientists were shocked when the probe, Viking 1, beamed back this image. Is that a human face? Perhaps produced by Martians in their own likeness? Until recently, we've never really known where to look in our solar system for extraterrestrial life. But we've always known what the aliens would be like once we found them.
Consciousness. I was on a table.
Usually, there is more than a hint of the Earthling in our aliens. Hostile or lovable, they tend to resemble mutant images of ourselves. As a senior astronomer at the Search for Extraterrestrial Intelligence Institute in California, Seth Shostak has spent his career listening for the radio waves of a distant alien society.
There's no reason to assume that they're going to look like us or even think like us or behave like us or have language. You know, you just have to look at the variety of life on Earth and you see that, you know, nature can come up with lots of different forms.
But if there is life on Mars, how could it survive in such extreme conditions? Since the 1960s, scientists have sent dozens of probes to the Red Planet. The first pictures of the barren landscape quickly dashed any hope of finding intelligent beings. But what scientists did see startled them. Though there's no evidence of Martian-made canals, there are signs that Mars actually may have had water. Some think the angry red planet might once have been blue.
You just have to look back a couple of billion years, 3.5 billion, 4 billion years ago. Mars had a thicker atmosphere, had water on its surface clearly. Maybe it developed life. And as it slowly went bad, you know, the life had to adapt.
Life may have adapted, not died off, because some liquid water may still exist underground. But with no surface water, frigid temperatures, and ultra-thin atmosphere, Mars is a planet only one kind of creature could love, an extremophile. Extremophiles thrive in the cruelest of places. To see where they might lurk on Mars, we head to the Valles Marineris, a massive rift in Mars's surface, 20 times wider than the Grand Canyon in places, and almost as deep as Mount Everest is tall. Lakes may have once flooded this valley, and those lakes could have hosted life. As the water dried up, life could have evolved to cope with the harsher environment. We won't know what these extremophiles are like until we find them. But they may resemble creatures that exist in extreme places right here on Earth. An unusual team of biologists, called astrobiologists, study Earth for the kinds of life we may find in outer space. Astrobiologist Rocco Mancinelli is on the hunt for Mars's extremophiles.
If it went beneath the surface, and some of it undoubtedly did, then what happened to it? Well, it formed brine pockets. So what kind of organism can live in a salty brine? A salt-loving organism.
Astrobiologist Chris McKay thinks he knows the kind of salt-loving creatures that might survive on Mars. Creatures much like those he's found in one of the driest, saltiest places on Earth.
The fundamental challenge to life on Mars is, in a sense, the fundamental challenge of life here in Death Valley. It's dryness. That is the hardest thing for life to adapt to.
Thousands of years ago, a salty lake covered Death Valley, just as lakes filled Mars's Mariner Trench.
This is still wet, a little wet.
This appears like a lifeless place, a big, flat, white, empty horizon. But yet, just below the surface, we find layers of algae and bacteria growing. They're living in an environment that in many ways is fundamentally different from the environment that we sense on the surface. Here you're in a place which looks lifeless, looks dead, and yet you dig down and hidden underneath, there it is.
Beneath the salt is a layer of hardy green algae that survive on the water and light that trickle through. The algae in turn feed salt-loving microorganisms.
Here in deserts on Earth, dried, salty lake beds, we're going to find them on Mars as well.
Salty deserts are not the only places life might be hiding on the red planet. There are Mars's tremendous volcanoes, some of them 6 times larger than those on Earth. Astrobiologist Penny Boston studies the caves, called lava tubes, left over after volcanic lava has dissipated. Not long ago, we assumed caves like these were devoid of life. They get no sunlight, and no sunlight means no photosynthesis. But in lava tubes outside Albuquerque, New Mexico, Boston has found evidence of extreme life.
Because we know Mars has many, many lava tubes. And so here we have the opportunity to see how these formed and also to look at the life that inhabits them.
The extremophiles Boston has found appear to be thriving. They get their energy by feeding on the minerals in the cave wall.
So here we're up close to the wall, and you can see these white patches here growing against the black basalt. And each one of these is like a major city for these little guys. And they're all nestled in these little pockets in the basalt. And so these guys are permanently adapted to these freezing temperatures. They never see any light, and they get what they can find in the environment.
Are there creatures like these in the caves below Mars's volcano fields? Boston thinks so.
We are going to find life, and I just hope that I live a long and healthy life so that I can still be around to see that.
We may already have had our first glimpse of Martians, not from our visit to their planet, but from their visit to ours. 16 million years ago, an asteroid slammed into Mars and propelled a 2-kilogram rock into space. Amazingly, that rock sailed to Earth and came to rest in Antarctica. Inside, NASA scientist David McKay and Everett Gibson were amazed to spot the outlines of fossils. Water has carved small tunnels in the rock. And in these tunnels, McKay and Gibson found what they believed to be evidence of bacterial life.
These are little microbes, and they're dead, and they're fossils, or in some cases, we don't even see the forms. We see the footprints or the evidence that they were there.
Life from Mars? Maybe. The hunt is only just beginning. NASA plans to send a rover called Phoenix to Mars. It will study the planet's ice cap and probe 3 feet beneath the surface. NASA even has a plan to send human visitors. They may not meet the little green men of our imaginations, but they could encounter life in some form. What will it look like? It is likely to be a subterranean dweller with an ability to survive on little water. Perhaps an organism with a taste for minerals, like the creatures in the lava tubes of New Mexico. Even the smallest find would have enormous implications. Proof that life is not unique to Earth, but exists just next door. Our safari to the places in our solar system likely to harbour alien life now takes us past the asteroid belt on the far side of Mars. Here, Jupiter reigns. But this planet, the largest in our solar system, is fairly hostile to life, thanks to its toxic gases and overpowering gravity.
Not only is it pretty cold out at Jupiter, it's also, it's got this really thick atmosphere, tens of thousands of miles thick, and it's got ammonia and methane and, things used to clean the bathroom. But Jupiter has more than 60 moons that we know about.
At first glance, those moons would seem unlikely places to seek alien life. Their atmospheres are thin, and they are inhumanly cold. The temperature on Callisto is lower than -200 degrees Celsius. The scientific probes Voyager and Galileo have detected little on the surface of these moons but ice, with one dramatic exception. Io is one of the closest moons to Jupiter. When NASA sent Voyager 1 to Io in 1979, astronomers were astonished to find its surface roiling with giant volcanoes.
Io is the most volcanically active place in the solar system, just spewing volcanic material from its surface all the time.
What could be heating the interior of this frigid moon? Amazingly, it's the force of gravity from Jupiter. The giant planet exerts enormous gravitational pull on its moons. The closer the moon, the stronger the force. So strong, it can actually stretch their crusts. But some of these moons have elliptical orbits, so as they near Jupiter, the crust stretches towards it. When they move further away, the crust relaxes back towards spherical. This constant tidal movement creates friction deep inside, and that friction generates heat. It's like rubbing two sticks together to start a fire. The pull of Jupiter is heating Io from the inside out. Volcanic fumes and lack of water make Io inhospitable to life. But Jupiter's other large moons are more distant, close enough for Jupiter's gravity to warm them from within, but distant enough to remain calm on the surface. 3 of them look particularly promising as possible homes for alien life. The one furthest from the giant planet, Callisto. On its surface, Callisto looks like our moon, scarred and cratered by countless hits from asteroids. Those impacts may have melted the surface ice for brief periods, allowing life to take hold. But in 1998, the Galileo spacecraft detected a much more promising incubator deep beneath Callisto's surface. Radioactive rocks and tremendous pressure in its core generate heat inside Callisto. The heat may be melting its icy crust from below, creating a hidden ocean. And hidden oceans could mean hidden life. As we fly closer to Jupiter, we find its largest moon, Ganymede. Ganymede is also deeply scarred. Ridges rise above its surface. Those bright spots are craters as big as 5 kilometers across, and likely to be lined with frost. But these photos offer the most compelling clues to where life here might hide. They show flowing glaciers, glaciers that resemble those on Earth. Ganymede's moving glaciers could also be signs of heat within. So, like Callisto, Ganymede could also have a hidden ocean, buried beneath as much as 190 kilometers of ice. The third moon on this leg of our alien safari is the most intriguing. It is called Europa, and of the three, it resides closest to Jupiter. That proximity to the giant planet means Europa's core may be very hot, far hotter than Callisto's or Ganymede's. But its surface remains frigid, a potent combination for life, since there could be a temperate zone where they meet. Mammoth fissures scar Europa's thick crust of ice, a sign that ice is always shifting. On our own planet, we see the same cracks in the ice sheets covering the Arctic Ocean. Europa's crust may be riding the largest ocean in the solar system, an ocean twice as large as all of Earth's put together.
Now, those oceans, if they're there, and the chances are pretty good that at least some of them are, they've been sitting around for a long time, 4 billion years, a little longer, right? In 4 billion years, an ocean of water, do you think anything might have cooked up there? Well, it certainly seems plausible.
The environment in Europa's ocean is more or less as nice as the environment in our own ocean, as a place for living things to exist. Heck, things from planet Earth could probably live in the European Ocean.
But Europa's oceans would be very cold, even slushy. And sunlight never penetrates them, thanks to an icy cover that may be 16 kilometers thick. We might never have thought life could exist here, if not for a revolutionary discovery off the coast of Ecuador. Deep in the Pacific, biologists have found flourishing communities of tube worms, crabs, and even squid. These creatures are thriving despite complete darkness, extreme cold, and the pressure of the deep ocean. They feed on bacteria that take their energy not from the sun, but from chemicals erupting from the sea floor. We might find very similar volcanic vents on Europa, supporting their own web of life. To find out, NASA scientists would like to put a lander on the European surface. Some would like to send a cryobot, a robot that would melt the ice and release a probe into the liquid below.
That's not so hard to do. You just have to melt your way through. But you're going to have to melt your way through not a couple hundred feet, but maybe a dozen miles of ice. And send down a fishing line with maybe a video camera and a light bulb on it and look around.
In all that water, we can't rule out the possibility that very simple life forms have evolved further. We might even find creatures as advanced as some here at home. Most likely, however, we would find microbes. But even that would be a sea change in how we view the birth and growth of life. Europa was warm. What if the place is one of the coldest known? Or if its lakes flow with toxic chemicals instead of water? These are the worlds we find as our safari continues even deeper into space. As our safari in search of alien life sweeps by the ringed planet Saturn, we can see the violently swirling gases that choke its atmosphere. We can also feel Saturn's gravity, weaker than Jupiter's, but still formidable. We'll keep moving. We're not likely to find living things here. Saturn's rings are also extremely inhospitable. They're made of rock and ice, as small as a grain of sugar or as big as a house. But Saturn has many moons, 56 that we've spotted so far. Our safari heads first to one of those moons, a tiny frigid satellite called Enceladus, just 500 kilometers in diameter. Here, gravity is very weak, a fraction of that on Earth. And Enceladus has hardly any atmosphere. It reflects back into space almost all the sunlight that hits it, making it the shiniest object in our solar system. Until very recently, we also thought Enceladus was too cold to support life. It appears we were wrong. In 2005, after a 7-year journey, the Cassini spacecraft approached the tiny moon and detected something that stunned the mission's principal investigator, Caroline Porco.
So this was the picture that just, you know, grabbed us. Just was shocking.
Those are plumes made of water from a geyser. The geyser's steam and hot water hit the cold vacuum of space and explode into a jet of ice. With little gravity to rein it in, the ice cloud can grow as big as Enceladus itself. Porco has never seen anything like it anywhere else.
It's like a planetary explorer's dream to come upon a body like Enceladus. Those jets, those fountains, if you will, just spewing vapor and icy snow hundreds of kilometers above the south pole of Enceladus.
There's only one conclusion. Tiny, frigid Enceladus is piping hot within. Like Jupiter, Saturn's giant gravitational field tugs on its satellites, creating friction and heat within.
As far as we can tell now, it seems like an inescapable conclusion that there may be liquid water deeper down on Enceladus because it's warm. And the best models we can put forth right now to even explain the warmth, much less the jets, seem to indicate that you would get temperatures warm enough to melt water.
Heat, liquid water, even the furthest reaches of our solar system may contain the chemistry for life. What kind of creature could live in the steamy waters of a geyser? Thanks to hot springs back on Earth, we have some idea. At one point, we assumed nothing lived in the steam-driven fountains of Yellowstone National Park. But then, biologists discovered microbes in these waters. Microbes that feed on chemicals dissolved in the water. Today, we call them thermophiles. The hardiest can thrive in boiling water. Could there be thermophiles on Enceladus? To find out, our safari takes us in for a close-up of this extraterrestrial Old Faithful. It's too cold for anything to live near the surface, but temperatures there are minus 165 degrees Celsius. But what about the hot water inside? In the ice plume above Enceladus, Cassini's probes have found carbon dioxide and methane, chemicals that could feed life below. Just as the chemical-laden springs of Yellowstone feed microbes living there.
We have a body that very, very likely has liquid water in its interior, has shown us already it's got simple organic compounds, and you know, a whole host of things that make it, I think, a major body of astrobiological interest in our solar system.
If Enceladus has been a shock, astronomers have been astounded by another of Saturn's moons, Titan. It may be the unlikeliest to harbor life. Titan gets only a limited amount of sunlight, about 1,000th as much as Earth. Probes sent to Titan have detected ice, but no liquid water. And at temperatures of minus 138 degrees Celsius, that ice is hard as stone. What could possibly make Titan a promising environment for alien life? Remarkably, Titan in many ways resembles the Earth, but not the one we know now.
Titan has turned out to be the body fantastic in the Saturn system, which is long suspected of having an environment at the surface, not only similar to the kind of environment we find here on Earth, even, believe it or not, similar to the kind of environment we had on Earth before the emergence of life.
Titan intrigued Caroline Porco's team so much, they directed the Cassini spacecraft to send a probe there in 2005. It was the most distant surface mission ever conducted. probe saw just ridges and plains. But a later flyover by Cassini spotted a shoreline. Soon, thousands of lakes came into view, at least one bigger than the Great Lakes of North America. It's the first time we've ever detected liquid on the surface of another celestial body.
Kind of looks like Minnesota, except the lakes are not water. They're liquid natural gas. But liquid natural gas is a liquid.
And that's not snow. Those are methane flakes. Like Earth, Titan has weather. But it's of a rather psychedelic kind. There are even methane hurricanes.
It's not water, it's methane, doing all the exact same things. Raining, evaporating, flowing in rivers. So you have something that is basically doing what water does on Earth. On Titan, only it's methane.
A similar scene may have existed on Earth 4 billion years ago, making scientists suspect that Titan could also be an incubator for life.
Chemistry does go on. At those cold temperatures, it's really slow. But Titan has had 4 billion years in which to do some chemistry, and maybe in that period of time, maybe something is cooked up.
It would have to cook up without liquid water, something we've never seen before. But scientists aren't ruling it out. The substitute could be the methane, so abundant on Titan. Used for fuel on Earth, methane was long thought poisonous to all life. But in 1997, researchers examined mounds of methane ice in the Gulf of Mexico, and they were astonished to find colonies of small centipede-like worms thriving amid the frozen substance. They think the worms may eat bacteria that feed on the methane.
In general, things that we think of as deadly, many of them are potentially lively. If you can figure out an evolutionary way to tap into that energy rather than having it destroy you, then it can be bountiful.
There could be one more complication for life on the surface of Titan. With only a weak magnetic field to shield it, living things on the surface could be exposed to cosmic radiation. But that might not be a problem for an extremophile, as we found here on Earth. Biologists have uncovered plenty of life near Chernobyl's contaminated nuclear reactor. And even swimming in toxic radioactive spills, actually feeding off the decaying molecules. It's possible Titan's life forms could do the same. To find life on Titan, we may have to dive into its methane lakes, where we might find chemical-loving bacteria. We may even find microbes resistant to radiation, not unlike those here on Earth at Chernobyl, living on its rock-hard ice sheets. Organisms that eat methane might give off heat, melting the ice, possibly creating another fountain for life. There's no doubt, life on Titan would be a strange brew. But we have yet to visit the most bizarre world where scientists believe life could exist, and it's much closer to home. Our safari of the world's most likely to harbor alien life has taken us far. We've visited frigid deserts, submerged oceans, and methane lakes. But the world we are about to visit may be the most extreme of all. For our final stop, we are turning back toward Earth, to Venus, our closest planetary neighbor in the solar system. If life can survive here, it seems it could exist almost everywhere. To reach the surface of Venus, we have to fly through a dense layer of yellow clouds, 64 kilometers deep, with a composition similar to battery acid. The atmosphere here is 90 times heavier than Earth's, too heavy for a human to tolerate. On the ground, there are extinct volcanoes and lava flows as far as the eye can see. They cover 85% of the planet's surface. It is hard to believe Venus once had vast oceans.
You basically had a runaway greenhouse effect, where as it starts to get warmer, the oceans start to evaporate, and then that puts water vapor in the air. Well, water vapor is a potent greenhouse gas, so that's what leads to the runaway. The oceans basically boil off, and then the CO2 all ends up in the atmosphere, and so today you have this very hot, hyper greenhouse planet.
With temperatures around 460 degrees Celsius, Venus is even hotter than Mercury, the planet closest to the Sun. Not a surface hospitable to life.
Life, as we know it, cannot exist on the surface of Venus because organic molecules would just be ripped to shreds by the hot gases.
But we've stopped here, not because of what's on the ground, but what's in the air. In 1982, the Soviet spacecraft Venera 14 visited Venus. In the clouds, 50 kilometers up, it detected temperatures much cooler than on the surface. What's more, it found the molecules so critical for life, H2O. So far, every bit of water we've found beyond Earth is frozen solid. Only in the clouds above Venus have we found it in vapor form, a possible incubator for life. But Venus's clouds are also filled with highly acidic sulfur. Once, we thought nothing could live in sulfur. But scientists have analyzed some of the most acidic water on Earth, leaching from a California mine.
Watch your head.
In sulfuric acid strong enough to erode metal, eat through clothing, and dissolve human flesh, they found life. Acid-loving extremophiles. These organisms feed on sulfur compounds, like iron sulfide, eating the iron and emitting the highly acidic sulfur. Do extremophiles like these float above Venus? Astrobiologist David Grinspoon likes to think it's possible.
Maybe in the clouds of Venus there are some sulfur-based organisms. Sulfur actually absorbs ultraviolet light in interesting ways, and I'm just imagining that there's maybe some kind of photochemical reaction going on where ultraviolet light is actually being used to convert chemicals into some higher energy state, which then is basically being eaten.
What will these aliens be like if we do find them? They would have to tolerate high temperatures and enormous atmospheric pressure. They would also need to thrive in acid concentrations deadly to most life forms. Perhaps they might resemble a hardier version of the acid-resistant extremophiles in California's mine.
We keep finding that life lives in places that we used to think were inhospitable. So whenever we say, oh, it's impossible, you couldn't have life in the clouds of Venus, I think we have to be very careful because they might just reflect our own ignorance or our limitations on our own imagination, and maybe not real limitations on the ultimate creativity of nature, which seems to find solutions to these problems.
As our safari returns to the cool, blue, lush and lively world of Earth, we can see why we so revere its life-sustaining gifts. But, as we are learning, even the most extreme environments can harbor living things. Extremophiles may resemble the first version of life in our universe, and they could even be the most common. Could they have evolved further from these humble beginnings? Could intelligent life be out there as well? For more than 40 years, scientists at the Search for Extraterrestrial Intelligence Institute in California have been searching the skies for answers to that question. Astronomer Seth Shostak believes he'll know the sound of alien life when he hears it.
We have a couple of observing projects to try and find signals. The biggest one are our radio searches, and that's where we use big arrays of antennas, and we point these antennas at nearby star systems that we think, well, this is the kind of star that might have a planet that might be something like Earth. We point in those directions, hoping to pick up a signal that would tell us that somebody there is clever enough to build a radio transmitter.
It's a safari that never leaves home. Astronomers have also recently captured enough light from planets in distant solar systems to deduce their chemical makeup. They have found elements that may help form RNA, one of the building blocks of life here on Earth. And 20 light-years away, in the constellation Libra, a team of European astronomers has found a planet that could be warm enough to have liquid water on its surface, just like Earth. Meanwhile, headed to the furthest reaches of our galaxy are 4 spacecraft launched in the 1970s. Aboard 2 of them is a map of our solar system and the image of a man and a woman. 2 others carry a sample of uranium, whose rate of decay would date the probe, regardless of language. The 2 are also carrying what could be the most universal message of all, a recording that includes a composition by Bach. Just don't expect news anytime soon. These intergalactic postcards from the Earth will take 80,000 years to reach the nearest star. Our search for life beyond Earth has only just begun. There are billions of planets yet to be explored. Every one of them holds the tantalizing possibility of life. Even intelligent life.
Just in the face of this enormity, the idea that we're the only game in town, it just doesn't seem reasonable.
I think the question of whether we're alone is profoundly important for human beings in general. If you're aware, you really have to ask that question.
Somewhere in a galaxy, known or unknown, something or someone could be looking out into space, peering at the Milky Way and wondering, is there life out there?
In a great cosmic pinball game we call our universe. How does energy stitch the cosmos together? And how do we fit within it? We now climb the power scales of the universe. From atoms, nearly frozen to stillness, to Earth's largest explosions. From stars, colliding, exploding, to distant realms so strange and violent, they challenge our imaginations. Where will we find the most powerful objects in the universe? Today, energy is very much on our minds as we search for ways to power our civilization and serve the needs of our citizens. But what is energy? Where does it come from? And where do we stand within the great power streams that shape time and space? Energy comes from a Greek word for activity or working. In physics, it's simply the property or the state of anything in our universe that allows it to do work. Whether it's thermal, kinetic, electromagnetic, chemical, or gravitational. The 19th century German scientist Hermann von Helmholtz found that all forms of energy are equivalent, that one form can be transformed into any other. The laws of physics say that in a closed system, such as our universe, energy is conserved. It may be converted, concentrated, or dissipated, but it's never lost. James Prescott Joule built an apparatus that demonstrated this principle. It had a weight that descended into water and caused a paddle to rotate. He showed that the gravitational energy lost by the weight is equivalent to heat gained by the water from friction with the paddle. That led to one of several basic energy yardsticks, called a joule. It's the amount needed to lift an apple weighing 100 grams 1 meter against the pull of Earth's gravity. In case you were wondering, it takes about 100 joules to send a tweet. So tweeted a tech from Twitter. The metabolism of an average-sized person going about their day generates about 100 joules a second, or 100 watts, the equivalent of a 100-watt light bulb. In vigorous exercise, the power output of the body goes up by a factor of 10, 1 order of magnitude, to around 1,000 joules per second, or 1,000 watts. In a series of leaps by additional factors of 10, we can explore the full energy spectrum of the universe. So far, the coldest place observed in nature is the Boomerang Nebula. Here, a dying star ejected its outer layers into space at 600,000 kilometers per hour. As the expanding clouds of gas became more diffuse, they cooled so dramatically that their molecules fell to just 1 degree above absolute zero, the total absence of heat. That's around 1 billion trillionths of a joule. That makes the signal sent by the Galileo spacecraft as it flew around Jupiter seem positively hot. By the time it reached Earth, its radio signal was down to 10 billion billionths of a watt. Now jump all the way to 150 billionths of a watt. That's the amount of power entering the human eye from a pair of 50-watt car headlamps a kilometer away. Moving up a full 7 powers of 10, moonlight striking a human face adds up to 300 thousandths of a watt. That's roughly equivalent to a cricket's chirp. From there, it's a mere 5 powers of 10 to the low-wattage world of everyday human technologies. Put 10 100-watt bulbs together. At 1,000 joules per second, 1,000 watts, that roughly equals the energy of sunlight striking a square meter of Earth's surface at noon on a clear day. Gather 200 bulbs. 20,000 watts is the energy output of an automobile. A diesel locomotive, 5 million watts. An advanced jet fighter, 75 million watts. An aircraft carrier, almost 200 million watts. The most powerful human technologies today function in the range of 1 billion to 10 billion watts. including large hydroelectric or nuclear power plants. At the upper end of human technologies was the awesome first stage of a Saturn V rocket. In 5 separate engines, it consumed 15 tons of fuel per second to generate 190 billion watts of power. How much power can humanity marshal? And how much do we need? Long before the launch of the space age, visionaries began to imagine what it would take to advance into the community of galactic civilizations. In the 1960s, the Soviet scientist Nikolai Kardashev speculated that a Level 1 civilization would acquire the technology needed to harness all the power available on a planet like Earth. According to one calculation, we are 0.16% of the way there. This is based on British Petroleum's estimate of total world oil consumption, some 11 billion tons in 2007. Humans today generate about 2.5 trillion watts of electrical power. How does that stack up to the power generated by planet Earth? Deep inside our planet, the radioactive decay of elements such as uranium and thorium generates 44 trillion watts of power. As this heat rises to the surface, it drives the movement of Earth's crustal plates and powers volcanoes. Remarkably, that's just a fraction of the energy released by a large hurricane in the form of rain. At the storm's peak, it can rise to 600 trillion watts. A hurricane draws upon solar heat collected in tropical oceans in the summer. You have to jump another power of 10 to reach the estimated total heat flowing through Earth's atmosphere and oceans from the equator to the poles. And another 2 to get the power received by the Earth from the Sun at 174 quadrillion watts. Believe it or not, there's one human technology that has exceeded this level. The AN-602 hydrogen bomb was detonated by the Soviet Union on October 30th, 1961. It unleashed some 1,400 times the combined power of the Nagasaki and Hiroshima bombs. With a blast yield of up to 57 million tons of TNT, it generated 5.3 trillion watts, if only for a tiny fraction of a second. That's 5.3 yottawatts, a term that will come in handy as we now begin to ascend the power scales of the universe. To Nikolai Kardashev, a Level 2 civilization would achieve a constant energy output 80 times higher than the Russian superbomb. That's equivalent to the total luminosity of our Sun, a medium-sized star that emits 375 yottawatts. However, in the grand scheme of things, our Sun is but a cold spark in a hot universe. Look up into southern skies, and you'll see the Large Magellanic Cloud, a satellite galaxy of our Milky Way. Deep within is the brightest star yet discovered. R136A1 is 10 million times brighter than the Sun. Now, if that star happened to go supernova, at its peak, it would blast out photons with a luminosity of around 500 billion yottawatts. To advance to a level 3 civilization, you have to marshal the power of an entire galaxy. The Milky Way, with about 200 billion stars, has an estimated total luminosity of 3 trillion yottawatts. A 3 followed by 36 zeros. The author Isaac Asimov imagined a galaxy-scale civilization in his Foundation series. Galaxia, he called it, is a superorganism that surpasses time and space to draw upon all the matter and energy in a galaxy. But who's to say that's the upper limit for civilizations? To boldly go beyond level 3, a civilization would need to marshal the power of a quasar. A quasar is about 1,000 times brighter than our galaxy. Here is where cosmic power production enters a whole new realm, based on the physics of extreme gravity. It was Isaac Newton who first defined gravity as the force that pulls the apple down and holds the Earth in orbit around the Sun. Albert Einstein redefined it in his famous general theory of relativity. Gravity isn't simply the attraction of objects like stars and planets, he said, but a distortion of space and time, what he called space-time. How a totally dark object can do this has been narrowed by decades of observations and theory. If a black hole spins, it can turn into a violent cosmic tornado. Gas and stars begin to flow in along a rapidly rotating disk. The spinning motion of this so-called accretion disk generates magnetic fields that twist up and around. These fields can channel some of the inflowing matter out into a pair of high-energy beams, or jets. Gas and dust nearby catch the brunt of this energy, growing hot and bright enough to be seen billions of light years away. Amazingly, the power of a black hole can rise to even greater extremes at the moment of its birth. As a giant star ages, heavy elements like iron gradually build up in its core. As its gravity grows more intense, the star begins to shrink until it reaches a critical threshold. Its core literally collapses in on itself. That causes the star to explode in a supernova. And now, in death, the star can unleash gravity's true fury. In the violence of the star's death, gravity can cause its massive core to collapse to a point, forming a black hole. In some rare cases, the newborn monster powers a jet that accelerates to within a tiny fraction of the speed of light. For a few minutes, these so-called gamma ray bursts are known to be the brightest events since the Big Bang. 3 orders of magnitude above a quasar, at a billion yottawatts, a 10 with 42 zeros. Remarkably, they are still not the most powerful events known. Albert Einstein's equations contained an astonishing prediction: that when massive bodies accelerate or whip around each other, they can stir up the normally smooth fabric of space-time. They produce a series of waves that move outward, like ripples on a pond. Scientists are now hoping to detect these gravitational waves and verify Einstein's prediction using precision lasers and some of the most perfect large-scale vacuums ever created. At the Laser Interferometry Gravitational Wave Observatory, known as LIGO, they are hoping to record the collision of ultra-dense remnants of dead stars known as neutron stars and of black holes. According to computer simulations, as 2 black holes spiral into a fateful embrace, the energy carried by each gravity wave rises 5 orders of magnitude above a gamma ray burst, to 100 billion trillion times the power of our Sun. Does the collision of black holes define the known power limits of our universe? Perhaps not. As turbulent as the environment of a black hole might be, its true power may well lie deep in its core. A black hole's mass is enshrouded within a dark sphere called the event horizon. Since the 1920s, scientists have described the mathematics of the event horizon as the equivalent of a waterfall. It's the point of no return, beyond which water falls freely into the gorge. At the event horizon of a black hole, space itself falls freely in at the speed of light. If the black hole is spinning, then the flow spirals down and around an inner horizon that envelops the singularity. That's the central region where space-time becomes infinitely warped. Any matter that rides this river of space whips around the inner horizon so fast that centrifugal force tends to fling it back out. As that happens, it collides with matter that's streaming in, whipping up a ferocious cosmic storm. The energy of the colliding stream feeds upon itself, rising to what may well be a limit imposed by nature. It dissipates only as it falls into the singularity and disappears. Fortunately for us, gravity walls off such energy extremes behind the event horizon, where they cannot affect the rest of the universe. And so, here we sit. Our world is nestled within a vast stream of cosmic energy, somewhere between the spin of an electron and the maelstrom of a black hole. There's no telling whether a future Earth civilization will be able to harness enough energy to advance into the cosmos. For now, as we tap into the tiny morsels of power at our disposal, we venture a closer look at a universe blazing with activity. We are its product, and its starstruck admirer.
From the sun. For centuries, we humans have gazed at our neighbor and imagined an alien world. And as human technology advanced and telescopes brought it closer, we began to see signs of life.
As the 20th century began, mainstream credentialed astronomers were looking at Mars, thinking that they saw evidence for a society, a civilization on the red planet.
We Earthlings braced for contact. If there was life on Mars, what form would it take? We set off into space to find out. But as we approached the red planet, we discovered a new mystery.
All the elements needed for life were there, so what happened? Where did everybody go?
Mars is almost Shakespearean, a beguiling world. It's tricking us every way.
So Mars, dead or alive? Some think Mars was home to an ancient civilization.
There was at one time intelligent life on Mars, and they built something.
But the evidence continues to elude us.
If there's life there, we'll find it.
Across the globe, the race is on for the greatest discovery of all. Join skeptics and believers alike as we try to answer the age-old question, is there life on Mars? If you're planning a trip to the planet Mars, here are a few travel tips to help make your journey as comfortable and rewarding as possible. All in all, the expedition will take about 2.5 years, including approximately 12 months aboard your interplanetary spaceship. So make yourself comfortable. Plan your provisions carefully. You'll need to bring plenty of water. At this time, there's no liquid H2O anywhere on the planet's surface. You'll also need an effective spacesuit and a sufficient supply of breathable air. Finally, remember, Mars is about 1.5 times further from the Sun than Earth, which makes this a cold world. The temperature can drop to a chilly -130 degrees Fahrenheit. So dress warmly. These technical issues aside, Mars has a lot to offer. It is home to the largest known volcano in our solar system, a magnificent Grand Canyon, and breathtaking deserts. For those of you interested in culture, a visit to the notorious Face is a must. We know you have a choice, so thank you for choosing the planet Mars. All in all, without ever setting foot on Mars, we know a lot about this distant world. But what we don't know is, what about life? When the first astronauts arrive on Mars, who or what will they find? Will aliens be there to greet us? Or is no one there at all? Inquiring minds want to know, is there life on Mars? It's a big question, and a fundamental one. Because really, it's synonymous with the question of, are we alone in the universe?
If we go to Mars and find evidence that there was life on Mars or is life on Mars, then we'd be able to say that in our own solar system, life appeared twice. I think that would be convincing evidence that the universe is full of life.
Discovering life on Mars could also reveal a lot about our own existence.
We have one kind of life adapted to one planet, even with all of its diversity. So looking at the way other planets may have given rise to a phenomenon that we would recognize as life can enable us to understand our own kind of life in a deep and fundamental way.
The stakes are high in the game of life, and Mars may hold the key.
If we're going to find proof of life on Mars, we're going to have to go to Mars to get it.
But getting to Mars isn't exactly easy. The Apollo astronauts took about 2 days to get to the Moon. A journey to Mars one way is roughly 7 months. Mars takes about twice as long to orbit the Sun as Earth. So a space mission has to plan departure when the two planets are close. The challenge of bringing a mission back is incalculable in complexity. Just one of the reasons no manned mission has ever been attempted. But that's exactly what Dr. Robert Zubrin of the Mars Society wants to do. Bob Zubrin, an astronautical engineer with 15 years of experience in the space industry, has been planning a trip to Mars for the last 2 decades, and he's come up with a novel way to do it.
If we want to go to Mars, we need to travel light, live off the land.
What makes a Mars mission so prohibitively expensive is the amount of mass, mostly rocket propellant, you have to send there and back. Instead, Dr. Zubrin came up with the following plan. Take supplies enough to get there, then make what you need on the planet.
There's 3 things we want to make on Mars. First, most importantly, propellant. After that, water. And third, oxygen. We can make all 3 with this machine.
Here's how the machine works.
The Martian atmosphere is 95% carbon dioxide gas. We pump that into the reactor. We mix that with a little bit of hydrogen. You can make that reaction produce either methane or carbon monoxide or any mixture of the two. And water.
The methane and carbon monoxide mixtures can be used as rocket propellants for the return trip to Earth.
The water, we could keep the water and drink it, or we could electrolyze it into hydrogen and oxygen. The oxygen that comes off, we could use as breathing oxygen, we could use as rocket propellant oxygen. That's how the machine works. It makes your fuel, it makes your oxygen, it makes your water.
And leaves enough room on your spaceship for food. All in all, it looks simple enough, and it's not just theory. Working with simulated Martian air, Zubrin has spent years testing and refining the technology.
This is a subscale methane, carbon monoxide, oxygen rocket engine. It all works. It works great. These are great propellants. We start them right up with a spark plug time after time.
In a way, Zubrin has done all this to make a point. Current thinking is that it is too expensive and dangerous to send a manned mission to Mars. Instead, the international space community has deployed a range of unmanned robotic explorers on and around the planet. But Zubrin points out using robots to do field research leaves a lot to be desired.
Okay, we can send robots to Mars. And I support sending robots to Mars. I think we want to send a lot more robots to Mars. Okay, robots can make all kinds of discoveries. They can give us all kinds of data. They can image the surface of the planet and possibly identify interesting targets for exploration. But they won't tell us the answers that we need to know. They won't tell us if there's life on Mars.
So does Zubrin expect to find life on the red planet?
I think that a naturalistic view of the universe would suggest that the Earth is not special, and that if life can evolve here, it could evolve elsewhere where environmental conditions are similar. And if there's life there, we'll find it.
But perhaps there's an easier way to find out. The answer could already be here on Earth. Every year, hundreds, maybe thousands of aliens come to our planet. Most arrive quietly and go unnoticed. Others enter the atmosphere in a blaze of glory. These aliens are meteorites. For centuries, these rocks from the sky were treated as curiosities, often ending up in local museums or private collections. But the information meteorites contain is so valuable that today, the scientific community sends out search parties to gather them. Although meteorites fall randomly all over the Earth, one of the most popular hunting grounds is Antarctica. Every year, scores of scientists take their lives in their hands and head to the frozen continent. The teams conduct a systematic grid search of the icy landscape. looking for telltale dark shapes against the blue-white of the ice. It was on an expedition such as this that a meteorite was found that would shake the scientific community to the core. The team sent it to a special facility at the Johnson Space Center in Houston, because this is where NASA keeps the aliens. 84001, or the Allen Hills meteorite. The strange green rock was kept under strict quarantine. It was processed, examined, and rigorously interrogated for information about its home world. It took 10 years, but investigators finally got the truth. This rock was from Mars, and it had a secret to tell.
Today, Rock 84001 speaks to us across all those billions of years and millions of miles. It speaks of the possibility of life.
So what was it the rock told us? We'll come back to that a little later. But perhaps the best evidence of life on Mars is not hidden deep in an alien rock. There are some who believe a vital clue is staring us right in the face. Richard Hoagland has dedicated his life to examining imagery transmitted to Earth from various Mars orbiters. Surveillance systems that have circled the red planet for over 30 years now. In the first pictures that the 1976 Viking orbiters sent back from the planet's surface, Hoagland saw something that blew his mind.
I looked at this and it was like, oh my God. This thing had symmetry, it had proportion, it looked like a statue.
Hoagland is referring to this remarkable image, a face-like structure the size of multiple city blocks. And Hoagland thought he saw more. Other structures surrounding the icon, eroded by time. To him, it looked like the ruins of a monumental city.
It looked eerily like an aerial photograph taken flying over Giza, looking down at the pyramids on the Giza Plateau. It looked like a ceremonial complex built by somebody with a huge sphinx-like creature staring up into space from the sands of Mars at the telescope orbiting 1,000 miles overhead. Somebody was down there, and they cared enough to leave the very best.
Needless to say, Hoagland's theory raises more than a few eyebrows. But did life on Mars ever exist? Was there once an ancient civilization of alien life forms? And if so, where did they go? Believe it or not, the idea that Mars was occupied by a race of intelligent extraterrestrials was not the creation of science fiction, but science fact. In the early days of humankind, Mars burned faintly red in the night sky, leading some to equate it with a mighty god, naturally, the god of war. But then astrologers, using a new contraption called the telescope, determined that those lights in the sky might be planets, much like ours. This meant there might be other civilizations, other life forms out there. And Mars was about to become the star attraction. Thanks to Italian astronomer Giovanni Schiaparelli. In 1877, Schiaparelli trained his telescope on the Martian surface and observed the existence of canali. By this, he meant natural channels. But due to an unfortunate translation, these channels became canals, which implied a man-made phenomenon. To fully understand the impact of this, consider that only a few years earlier, human engineers had completed the awe-inspiring Suez Canal. It defied nature and geography by linking the Mediterranean and Red Seas. It was considered the latest wonder of the modern world. Whether or not Schiaparelli believed the canals to be made or natural, the word itself sparked the public imagination. If there were canals on Mars big enough to see from Earth, really intelligent beings must have built them. The rumor was dramatically compounded by an American astronomer named Percival Lowell. Lowell was a highly respected man of good society who had a profound love of astronomy. He developed a fascination with the canals of Mars and sat up through the nights observing the red planet. And what Lowell thought he saw in the wee hours was a dying world crisscrossed by constructed waterways. Perhaps, he wrote, creatures short on water have built an irrigation system that circled the planet. By the turn of the 20th century, the idea that Mars was occupied had hit the mainstream media. New York Times headline, 1911, Martians build 2 immense canals in 2 years. Martian civilization was usually perceived as being ahead of us in evolution. And each earthbound nation projected onto Martian society the diverse vision and fears of its own future. In this 1924 movie from Russia, Mars is portrayed as going through a proletariat revolution and ending up successfully communist. But many thought that Mars was dying, and some said it was only a matter of time before Martians tried to contact us. And so, some thought, they did. Through another new technology.
This is Seth Shostak. Go ahead, caller.
Radio. Astronomer Seth Shostak takes up the story.
It goes right back to those early radio pioneers, and none so directly as to Nikola Tesla.
One of the most brilliant electrical engineers of all time, Nikola Tesla, was the first to claim someone from beyond this planet was trying to get our attention. In 1899, Tesla was experimenting with an electric invention that essentially acted as a large antenna when he noted something strange. Repetitive signals which were substantially different from the signals he had noted from storms and earth noise.
And it's only natural to imagine that he would ascribe this to some sort of intelligent beings, because as far as Tesla knew, only transmitters could make radio sounds. So he naturally assumed that if he heard something, somebody was broadcasting it.
In fact, Tesla was probably mistaken, as Shostak often gets to explain on his weekly SETI radio show.
Well, we don't know for sure what Tesla heard, but most likely it was something that we call whistlers. These are just distant thunderstorms, lightning discharges that produce natural radio waves that get distorted by the atmosphere as they propagate around the Earth and make a sound that kind of sounds like a whistle.
Modern science may have an explanation, but in a way, Tesla was ahead of his time. The idea that you could send signals from one planet to another made sense and inspired subsequent radio enthusiasts to listen for signals from outer space.
A guy by the name of David Todd realized that in 1924 there was a real opportunity to listen for the Martians. And the reason was that in 1924 you once again had one of those circumstances where Mars and the Earth got close to one another. So he organized an effort to get people to stop transmitting for 5 minutes every couple of hours so that people with the right equipment could actually listen, and this included the military, to listen for signals that might be coming from Mars or some other planet.
But whatever the message might have been, it seems we humans didn't get it. At which point, the Martians turned nasty.
Ladies and gentlemen, we interrupt our program of dance music to bring you a special bulletin from the Intercontinental Radio News.
In 1938, Mars attacked. Turns out it was apocryphal, an imaginative radio play based on the H.G. Wells book, War of the Worlds. But many believed it and thought Earth was under imminent threat from aliens.
Now, mind you, it wasn't so unreasonable. I mean, there were places that really were being invaded at the end of the 1930s, after all. So the mindset of the public was kind of attuned to the idea of hostile forces coming in and taking over.
And sure enough, they came. Martians, great and small, came out of the skies and landed in our movie theaters. Sometimes they looked like giant insects. Mostly they seemed suspiciously human-like, and they came in a bewildering variety of shapes and sizes. They had laser guns, evaporators, death rays, and deadly kisses. They wanted gold, weapons, earth women, and human blood. One thing's for sure, they were very rarely friendly. Next thing you know, real flying saucers were being reported from San Fran to Timbuktu, and the phenomenon of alien abductions was born. The world, it seemed, had gone crazy for extraterrestrials. For all its downside, the popular imagination paved the way for mankind to make that giant leap. In 8 years, the U.S. built a transport system and became a spacefaring people. Perhaps we were determined to bring democracy to the communists on Mars. In fact, we only got as far as the moon. And while there were no aliens up there, you might argue that if we could make the trip, then extraterrestrial life capable of interplanetary flight was at least a possibility. So what about Mars? As our technology got better, we sent a robotic scout to the red planet. The landing was a success. The robot touched down, turned on the camera, and we finally got a good look at Mars. It wasn't what we expected.
How disappointing after centuries of assumption that Mars was inhabited, that it had cities, it had canals, and the reality was that it was just this terrible, awful, dead-looking place.
Ladies and gentlemen, we regret to inform you, Mars is dead. Or is it? Mars may be unoccupied now, but if we're to believe Richard Hoagland, the red planet once hosted a magnificent civilization. Hoagland is the principal investigator of the Enterprise mission, a loose collection of scientists, researchers, and Mars enthusiasts. They've spent years trying to prove this extraordinary theory. For Hoagland, it boils down to this.
If I had one catchphrase to describe the whole problem of convincing scientists that there is really an ancient civilization on Mars, it would be, it's the geometry.
Take the face-like structure from this 1976 Viking orbiter image. NASA claims it's a naturally occurring rock formation. Richard Hoagland thinks there's more to it.
If you actually look at proportions, where the mouth is, where the nose is, where the eyes are, they conform to commonly accepted statues and representations of human forms that go back literally thousands of years.
And Hoagland has found what he believes to be a highly complex geometric relationship between various structures centered around the face. Hoagland claims that the layout of this region, named Cydonia, is similar to what we see in ancient ceremonial complexes on Earth.
There are alignments, there's parallelisms, there's right-angle rectilinearity. They also appear to have a specific geometric relationship to the face, to another massive structure down here, to other structures.
To prove his theory, Hoagland and his colleagues have applied a series of computer image analysis programs, looking for, well, basically things that don't match the surrounding landscape. And the face and a couple of other structures register as anomalies, implying, he says, artificial constructions.
This is the real image, and this is the fractal representation. And again, it's the signal strength is basically...
Strictly speaking, a computer will find whatever you program it to look for. It doesn't actually determine whether or not the artifact is natural. But Hoagland claims there are some things you can see for yourself. Take this pyramid, an apparently perfect tetrahedral form with an accurate apex and sharp angles.
This unquestionably had to be made by someone because nature does not produce this kind of structure. If we were to land someday, find the entrances to this thing, walk inside, because if the exterior is preserved in this extraordinarily pristine form, imagine what waits us on the inside.
But if there was a civilization, what happened?
That's where things get interesting, but that's where we obviously cross the line from science to speculation. We have no ground truth, unfortunately.
So why isn't NASA all over this? Hoagland thinks the government is hiding something.
I believe there's a cover-up. Call it a conspiracy if you will, except they're not called conspiracies, they're called policies.
And why? Well, according to Hoagland, it goes back to an obscure Brookings Institution study commissioned by NASA and published in 1960.
There is a section devoted to the implications of NASA's discovery of extraterrestrial life. And the document recommended that if we were to discover, i.e. NASA were to discover evidence of extraterrestrials, that it should be basically kept secret because it had the potential at the limit to destroy civilization.
The argument seems to be that where a civilization comes into contact with one more technologically advanced, that civilization's in trouble. So does this mean the government is covering up aliens to prevent a societal meltdown? It's a bit of a stretch when you consider that all the Brookings report actually suggested was that we should do more studies. Hardly sinister stuff. Seth Shostak thinks there's a fundamental flaw in Hoagland's cover-up theory.
Well, doggone it, if the aliens are really here and they're really advanced and they're really malevolent, as they could conceivably be, then it really doesn't matter what the government does it? This is Bambi meets Godzilla, and Godzilla's going to win.
This from someone who believes there's life beyond Earth. Shostak works for an organization that operates on the assumption that not only is there life out there, some of it has technology. This is the Allen Telescope Array, built and operated by the University of California at Berkeley and the SETI Institute. SETI stands for the Search for Extraterrestrial Intelligence. It may seem out there, but SETI is an entirely scientific operation, manned by astrophysicists, engineers, and planetary scientists. Their objective is simple.
It's really easy to send signals between the stars. That's the bottom line fact. There might be thousands, millions, or more societies that are sending information from one star system to the other. Why not look for it?
SETI is essentially eavesdropping on the universe in an attempt to pick up a signal from outer space. To do this, SETI uses highly sensitive radio receivers that scan systematically through the billions of star systems in our universe. It's like scanning through your car radio dial as you travel cross-country, but on a cosmic scale.
Now, what kind of signal are we looking for? We don't care. Looking for the message requires a different kind of technology that we haven't built and won't build until we find that they're on the air. We're just looking for a signal that tells us, hey, their transmitter switch is on.
It may seem like looking for a needle in a haystack, but astronomy has made enormous progress in identifying the stars and planets beyond our solar system, which, combined with ever-improving technology, allows SETI to search with more precision. The motive, however, is as old as mankind itself.
We're trying to look for something that would show that, you know, we're part of a bigger picture. We're not just a little bit of chemistry run amok on this small little world tucked away in the corner of a nondescript galaxy in an enormous universe.
So the million-dollar question, of course, has SETI made contact?
In 1997, we picked up a signal using a telescope in West Virginia that looked like the real thing. And we got quite excited to the point where everybody was glued around the computer monitors just looking at what was going on.
The signal had all the qualities SETI looks for in an alien contact. It occurred on a very narrow frequency. This is key because while nature produces radio waves aplenty, they are like broad static across the dial. This one was emanating from a specific location in the cosmos. Throughout the night, scientists were on the edge of their seats trying to pin down the source.
I realized that the world from that day forward will really not be the same. I was very nervous, actually, because I didn't know what the consequences were going to be.
It took 3 days, but the engineers and scientists finally identified the signal, and it wasn't alien.
As it turned out, the signal was due to a European research satellite, the SOHO satellite, the signal of which had just gotten into the structure of our antenna. And that was a bit disappointing.
In conclusion, then, the industry experts, SETI, have not yet found any evidence of extraterrestrial intelligence.
As of now, one thing you can say, and that is we have not conclusively proven the existence of any life, intelligent or not intelligent, beyond the bounds of Earth.
And what about Mars? Martian monuments aside, you'd be forgiven for thinking that 30 years of remote observation has done nothing but confirm our nearest neighbor is dead. But in fact, life on Mars has begun to make a comeback. It's all about water. When NASA scientist Chris McKay saw those 1976 Viking images of a dry, barren Mars, he was intrigued.
I remember the overwhelming impression I got was the lights are on, but nobody's home.
What McKay is referring to is what he poetically calls the ghost of water past. He's offered to meet us in the Mojave Desert to explain.
There's no water in this lake bed now, but the geology, the surface of the ground, shows evidence that there was water here. And that's what we see on Mars. We see dry lake beds. We see river beds that have no water in them, but clearly did at one time. And this is the evidence that Mars had water. And it's that water that's of interest to us from a biological point of view.
Although, in fact, the Mojave gets a whopping 5 inches of rainfall every year, Dr. McKay uses this desert as a near waterless zone to conduct experiments relevant to his theory about Mars. And life, it seems, can thrive nicely in these conditions.
We find microscopic life, microscopic algae, that have learned to survive under dry conditions. This organism, this algae, is the dry version of pond scum. They wait out in the dry for months, maybe years, and then a rain comes and they very quickly set up shop and do their biological thing, and then it gets dry and they shut down and wait again.
Dr. McKay certainly isn't claiming that Mars is populated by desert algae, but he thinks the odds are in favor of past life.
If we were to imagine what would the last Martian have been like as Mars went from a fairly wet, Earth-like environment to the dry desert that it is today, it would have been probably an organism like this.
Microbes? So much for the Martian monsters of the silver screen. But microbes bring us full circle. The fact is, some scientists believe we've already found life on Mars. And it's all because of mysterious clues in a Martian meteorite. Turns out our favorite Martian may be more like our favorite microbe. The 1976 Viking mission to Mars was a triumph of modern space exploration. But one unexpected bonus was information that could be used to further study our alien visitors. The unidentified meteorites sitting in cold storage on Earth.
Well, we've had meteorites we've known were meteorites for 100 years, but we didn't know they came from Mars until Viking landed and measured the gases in the atmosphere, and scientists studied the gases in these meteorites and showed that they were the same.
But how does a Martian rock get to Earth? Scientists think that some explosion, probably caused by the impact of an asteroid hitting Mars, blasts a rock off the planet and into space. It then hurtles around our solar system until, if it's very lucky, it gets caught by the gravity of our blue-green planet and plunges to Earth. Imagine the odds. For NASA scientist Dr. Everett Gibson, this event began a remarkable voyage of discovery.
For one to have life, you have to have the presence of water, you have to have the presence of carbon, you have to have an energy source, and you have to have geological processes. All of these four fundamental things are seen within the Martian meteorites. So, the conditions could be right for life to exist on Mars, perhaps in the past.
And it seemed the NASA team was about to prove it. Thanks to that odd little meteorite, 84001, from Mars.
600 million years after this rock was formed in the crust of Mars, you get water percolating through the rocks, saturated in carbon dioxide from the Martian atmosphere. As the water basically evaporates away, it potentially leaves the carbonate behind.
So the meteorite confirmed that Mars had once been wet. But there's more.
The carbonates contain organic matter. The carbonates contained an iron oxide mineral, magnetite.
Here on Earth, magnetite, essentially magnetic crystals, are often produced by microscopic life forms. This was getting exciting. Using the most powerful microscope at their disposal, the investigators now looked even closer and got the surprise of their careers. They saw what looked like minute worm-shaped structures. Quietly elated, the scientists were cautious.
We said one explanation could have been biology operating. Could have been the signatures of something like a life process.
So was this finally confirmation of life on Mars? Well, from the moment they were announced, the microbes have been controversial. Critics say that the carbonates, organic matter, and magnetite crystals can be explained through other non-life processes, and many believe that the worm-like structures are actually clumps of a coating material used to examine the sample in the laboratory. Still, others point out that the rock could have been contaminated at any time. perhaps when it was lying around for thousands of years here on Earth. Nevertheless, the possibility of ancient Martian bacteria raised the ante on life on Mars. If once upon a time Mars was warmer and wetter and had some early form of microbial life, did it survive, thrive, and grow up to build like an Egyptian? Well, it's a nice idea, but seems unlikely when you consider that conditions on Mars are dry, radioactive, and extremely cold. How could anything survive in this hostile environment? But we could be underestimating the nature of life itself. Microbial life, that is. Believe it or not, astrobiologist Penny Boston is searching for life on Mars by dropping deep into this heart of darkness. This is a lava tube, a subterranean cave formed by underground lava flows during volcanic eruptions that occurred thousands of years ago. And Boston has someone she wants us to meet.
Sometimes they're in crevices, sometimes they're kind of hard to see.
Is this when the scary monster reveals itself?
Ah, there's one.
Actually, no. This is an extremophile.
We're looking for what we astrobiologists call extremophiles in this environment, and that means that they're organisms that are living in very difficult conditions. In this particular case, these organisms are living in a very cold cave right around freezing. They are making their living without benefit of sunlight, and there's almost nothing to eat in this cave.
In recent years, scientists have discovered tenacious microorganisms living in all forms of extreme environments. So if on Earth, why not on Mars?
We think that Mars is covered with lava tubes. We believe that by looking at organisms that live in these extreme circumstances on Earth, we can learn a lot about what to look for on Mars, and that similar Martian organisms may be able to persist on Mars in places very similar to this lava tube.
To find out, Dr. Boston has created her own little Mars environment biospheres, essentially exposing a range of microscopic Earth life forms to various elements to be expected on Mars.
They have been subjected to Mars-like levels of high ultraviolet radiation and Mars-like temperature cycles. We have given them atmospheric compositions from very low levels of carbon dioxide with nothing else to perhaps 1/10 the density of Earth's atmosphere, and tested them under those conditions.
And so far, she's isolated 36 different strains of organism that thrive quite happily. So in theory at least, life could survive the harsh conditions of Mars, except for one problem.
There's one thing for sure that we know, and that is that all forms of life on our planet require liquid water. We don't know if that's going to be true on other planets, but we think that where there's going to be life, there's going to have to be water.
This simple fact has helped scientists in the 21st century refine the search for life on Mars into a comprehensive strategy. Dr. Jim Garvin is chief scientist at Goddard Space Center and a veteran of NASA's Mars exploration program.
NASA uses a term, follow the water. Following the history and record and abundance and inventory of water is a wonderful way to search for something as tough, perhaps elusive, as life.
We already know that Mars was wet in its ancient past and has reservoirs of ice in the polar caps. But using remote sensing technology, NASA has found what could be evidence of a modern water cycle.
We've discovered tens of thousands of hillside gullies that clearly released a fluid, likely liquid water, in the extremely recent geological past.
They've also discovered that Mars has a vast underground reservoir of ice, spanning about 30% of the planet.
The reservoir of water under the surface may include liquid zones. They may be liquid under the ice caps, they may be liquid hundreds of meters deep, they may be liquid tens of meters deep. All that points to a modern liquid water cycle on Mars.
Where there's water, there could be life. And when it comes to the question of life, Dr. Garvin is a believer.
Absence of life in all senses of the word throughout time on Mars. Is that a possibility? I actually believe not. All the right building blocks, initial conditions, the same that we think persisted in early Earth, must have been at Mars. So, the tale of two planets. Where do they diverge?
It is this that drives the international space community to take aim at Mars. Over the past 30 years, dozens of unmanned missions have been launched. But the red planet has become something of a Bermuda Triangle, with roughly 2/3 of all missions ending in failure. Given the danger and high ticket price, plans for a manned mission have been delayed for decades. For Dr. Bob Zubrin, it's a dream that he refuses to let go.
NASA had plans to send people to Mars by 1981. Those plans were credible. We should have been on Mars a quarter century ago.
Bob Zubrin is president of the Mars Society, a coalition of scientists from all walks of the international space community. The Society has been lobbying Congress, NASA, and the government for years, determined to keep Mars exploration on the radar screen. And Zubrin has been practicing. The Mars Society has set up Mars analog habitation modules in the deserts of Utah and the remote landscape of Devon Island in Canada.
What we're doing at these stations are really what someone would call operations research. We're trying to find out what field tactics and techniques would be most usefully applied on Mars, what technologies would be most useful to the crew.
And Zubrin has more in mind than a quick trip across space. He plans to colonize the planet.
We're going to Mars because Mars is the planet that has on it the resources needed to support life, and therefore potentially someday human civilization.
For Zubrin, Mars is the new frontier.
Whether or not there has been life on Mars, whether or not there is life on Mars, there will be life on Mars. And it will be us.
Zubrin isn't the only one with plans for the red planet. Dr. Chris McKay champions another idea, essentially to kickstart the biosphere.
If we go to Mars and find that there is no life, then I say we might as well move in.
And in the case of Mars, that begins with warming up the planet.
Well, we know how to warm up planets. We're doing it on Earth.
By introducing preferably non-harmful greenhouse gases into the Martian atmosphere, we could start a chain reaction.
The effect of these gases would be to melt the ice, bring back the atmosphere, and restore Mars to the conditions it was billions of years ago.
Right. But if we're going to live there, we're going to need oxygen. Well, Chris McKay has that covered.
These organisms are known as cyanobacteria. It's a type of algae, a single-cell type of algae, that has a very long history on Earth. These were the organisms that first made the oxygen. And these organisms could do the same thing on Mars. Send them to Mars and ask them to change the world.
Cyanobacteria, the planet changers.
These are the little green men. They're not men, but they are little and they are green.
But wait, what about the pyramids? The supposed signatures of an ancient Martian civilization. What if the guys that built the face are coming back? Mars. Could that enigmatic face in the hills of Cydonia really be a calling card from a lost civilization? Ironically enough, we might pick up a clue at the World Science Fiction Convention in Southern California. No, we're not looking for Martian monument builders. We're here to meet astronomer Phil Plait, a scientist on a mission to provide participants with a healthy dose of science fact. Today, he's taking on the face on Mars.
Just so we're clear on this, it's a rock that looks like a face, and it's not even that good of a face. It looks like he's got, I don't know, Isaac Asimov.
Phil Plait is the creator of Bad Astronomy, a website and book dedicated to debunking what he calls pseudoscience. For him, the solution to this Martian riddle is elementary.
There's a trait called pareidolia, and it is the tendency to see faces in random patterns, and we see this all the time. You can find lots of features on Earth. I once saw Lenin in my shower curtain. It was just a water stain in my shower curtain, but man, did it look like Lenin.
Why do humans do this? One possible explanation for seeing faces in random patterns is that it's a survival technique going back to infancy. Unresponsive babies are more likely to be ignored or abandoned. So to make sure he gets mom's attention, a baby will seek out the image of a human face and gurgle adorably. Whatever the reason, Phil Plait thinks we can't always trust the evidence of our own eyes.
Our brains don't like random patterns. They want to find some sort of real pattern in the noise, in the randomness, even if it's not there. And so you can just take a collection of dots and you might see a head, or you might see Jesus in it. But that's just your brain trying to find a pattern desperately in something that is patternless.
If you take a closer look at the Martian terrain, the planet explodes with faces. Face-like patterns, Plate insists, not monuments to ancient civilizations. Richard Hoagland, the leading advocate for the theory of monuments on Mars, has countered this argument for years. He insists his theory is based on more than just a pretty face.
If I had to stake my entire almost 30 years now looking at this, that there was at one time intelligent life on Mars and they built something, I would say the geometry of Cydonia is now trillions to one against it being chance, and in any man's or woman's science, when you have that level of odds in your favor, you can say with relatively good backing that it's real.
Fair enough. Let's ask the scientist. NASA scientist Jim Garvin has this to say about geometry.
It is possible to construct geometric patterns between anything. There's an infinite number, in fact, of different affine geometric patterns between this feature and that feature and this feature and that feature. To read one as being the answer to this particular small patch of Mars is extremely challenging to me and to the science community.
But what about those interesting pyramids and tetrahedral-shaped landforms? Just the wind, says Garvin.
If the wind is blowing one way for a while, and the next season it blows this way, and the next season it blows this way, and the next season it blows this way, what happens? Over time, if that's the consistent pattern of the wind, sandblasting, in this case a hill about 10 blocks in scale, you can produce landforms that remind one of pyramids.
Similarly formed natural structures called yardangs are found in the dunes of Egypt's western desert. In short, Dr. Garvin sees the Cydonia region as a natural landscape shaped by the forces of erosion. So what about the face?
When I look at this picture on Mars, I see positive relief landform, a hill of the scale of multiple city blocks, very similar to tens of thousands of others on Mars.
But Dr. Garvin insists you can't prove anything with a two-dimensional snapshot. In order to analyze the structure, he's created a 3D model of the landform by combining topographical data with a high-resolution 2D image. Now he is able to observe the face as if he were flying around it in a helicopter. And from this height, the Sphinx dissolves into landscape. No eyes, no mouth. Remarkable only because this is a hill on another planet.
There's a lot of different interesting ways to look at this feature. The simplest way is the natural way. And that's always worked well in science.
Just one more thing. Why doesn't NASA send one of its robots to take a look? Well, considering the enormous cost and the physical challenges of dropping a priceless asset such as a Mars rover, the target must surely be chosen with careful consideration on the basis of scientific priorities.
Why would we consider this a first priority? And that's the question I leave you with. We're looking for our origins in the history of life in the universe. And there is no evidence that that has a bearing on that question today.
In the end, it's up to you to believe in the magic of ancient monuments or the world of modern science. So Mars. For centuries, the red planet has kept us guessing. First, it was home to an advanced civilization and the Martian invaders of our silver screen. Then, it was a cold, dry, barren planet. And now, it offers the possibility of life, with mysterious clues in a Martian meteorite and the suggestion of water once thought long gone. But is there life on Mars?
I think odds are we won't find life. There's no evidence, so I'm not going to bet my house either way.
But the desire to know drives us ever closer to an answer that may also hold the key to our very place in the universe.
We live in space as small, minuscule amounts of the matter that is the bigger space. The more we understand the history of life in this solar system, in this universe, the more we understand our own life and our own destiny.
It's been 30 years since a human last set foot on another world. If space exploration is to become a reality, not of the past, but our future, perhaps it's time to set our sights on Mars.
There's some moments in history where you have the capability of doing something important, and I think that this generation has the capability of finding out whether we're alone or not.
Either way, it's something we need to know.
If we search the universe and we find no evidence of life, we should start taking seriously the possibility that life on Earth is unique, really unique, and that in a very real way, the contribution of Earth to the rest of the galaxy, to the rest of the universe, may be life itself.
Alone in the vastness of space? Perhaps even the worst of our Martian nightmares is better than galactic solitude. One thing is certain. Our best hope for finding out if life exists in the universe lies on our sister planet, the Red Planet, the remarkable neighbor we call Mars.
From the chaos on the outer planets to the broiling heat of Earth's closest neighbor, radical weather is the norm in the solar system. We do have our own extremes here on Earth, but they pale in comparison to the fastest, dustiest, wettest, and most brutal alien storms. On Earth, the sun drives our weather, and sometimes drives it wild. When hot and cold collide in the atmosphere, watch out. This is true locally and globally. But storms on other planets are bigger, badder, and stranger than their counterparts on Earth. Why is that? Because of the sun? If not, what else fuels their fury? The basic laws of nature, the rules of the game, are pretty much the same wherever you go in the solar system. But every planet has its own way of playing the game. Right now on Mars, the entire planet is being covered in dust. This global dust storm blocks 99% of the sun's rays from reaching the planet's surface. It's actually a system of smaller but still massive storms churning dust high into the atmosphere. Once it starts, it takes months for Martian skies to clear.
Mars is just the most dramatic weather in the solar system in some senses. It's very rare in the solar system you get a weather event that can take out the whole planet.
So if the basic rules of hot and cold are the same on Mars, why is the weather so different from Earth? For one thing, Mars is half the size of Earth. It's also 50% further from the sun, so it's much colder. The average temperature on Mars is minus 80 degrees. That's almost 130 degrees colder than Earth. And the atmosphere is extremely thin and composed mostly of carbon dioxide. But perhaps the most important difference is this: Mars is a global desert.
What would Earth be like without water? Well, it'd probably have a lot of dust.
There's no liquid water at the surface of Mars, and there's very little water in the atmosphere, and so there's nothing to sort of keep the dust down.
On Earth, dust storms are localized and short-lived.
The reason for that difference in scale is that the storms are generating their own weather on Mars, whereas on the Earth, they're slave to the weather that's going on around them.
In other words, on Earth, the global weather system creates dust storms. On Mars, the storms create a global weather system. Astronomers have always been able to see big Martian dust storms easily with Earth-based telescopes. But what they couldn't see was what caused them. That would require a trip to Mars itself. In 2003, NASA landed 2 rovers called Spirit and Opportunity on the Martian surface. Their mission? To learn more about the geology of the red planet. NASA engineers always assumed that as these 2 vehicles roamed the Martian surface, dust would build up on their solar panels.
If you have a lot of dust that's falling down out of the atmosphere and coating the panels, pretty soon you're not getting much sun to the silicon. And in fact, we thought that that was what was going to kill the rover Spirit and Opportunity.
Only it never happened. The rovers didn't die as expected. As dust built up on the panels, somehow something would clean them off. But how could this be? NASA engineers were baffled until the rovers themselves saw the culprit. Martian dust devils.
It turns out that dust devils were sort of our white knight. They came along and cleaned off the solar panels just at the time we were expecting to start having some problems.
There are beautiful photos that actually show dust devils moving across the Martian atmosphere, and ghostly soldiers moving out there in the distance.
A dust devil is really an extreme form of rising hot air, or convection.
And that hot air wants to go up, and it comes up just like, water going down a drain. Well, this is air that just spirals up into the colder parts of the atmosphere.
Whenever warmer air, which is less dense, rises up through cooler air, which is more dense, it rotates as it swirls upwards. Convection can be very powerful, strong enough to lift things up. On Earth, it lifts moisture, and that's how thunderstorms form. But on Mars, there is no moisture, so it lifts dry, dark dust and creates giant dust storms instead. Once airborne, Martian dust clouds absorb sunlight and heat the atmosphere. This supercharges the convection, lifting still more dust.
That produces more winds, which bring up more dust, and these things can spread up to thousands of miles across, or even, in some cases, they can envelop the entire planet.
And because the Martian atmosphere is so thin, it doesn't take much to get this cycle going.
You get a lot more difference between the surface temperature and the air temperature, and so the convection on Mars is very much more vigorous.
As a rule, Earth doesn't get the temperature extremes that Mars does. But sometimes, here and there in the deserts of Earth, convection can be very Martian-like. And we get dust devils, too. But at Arizona State University, Lynn Necrace makes dust devils to order in a lab to study them up close. He uses a vortex generator and substitutes lighter, dry ice for dust. What he creates is not an exact replica of how real dust devils form, but good enough to see how they pick up dust and debris.
Natural dust devils usually form from the bottom up, as opposed to tornadoes, which form from top down. So what happens when we turn this on, we have the airflow starting, and as the airflow starts to rotate from the fans down to the floor, we actually end up having the vortex form.
In other words, the vortex generator, basically a huge vacuum cleaner, imitates the swirling action of convection.
You can see here there's a wider base where larger particles of the dry ice are being swept up and gets wrapped up and tightens as it expands upward. The center of the core is where the majority of the lifting would occur.
Martian dust devils have been helpful, keeping the rovers clean. But could they actually be making a mess of the rest of the planet? Some scientists think there are so many at any one time, and they lift so much dust into the atmosphere, that together they trigger these much larger dust storms.
It starts wind patterns, and the air's warmer over here, and it's colder over here, and the air starts moving around. Pretty soon you're spreading dust over the whole planet.
And we found measurements that indicate there's up to maybe 200 dust devils per square mile per day during some parts of the summer.
And they can range from a couple of 100 feet tall to devils that stretch 6 or 7 miles high.
You can get just towering monsters of dust devils that we would never see on the Earth. The kind of maximum sized dust devils you see on Mars are more like tornadoes on the Earth, where they're going up almost 10 kilometers. So these things are just real monster systems.
Back at Arizona State University, scientists blow crushed walnut shells as silicate particles in the Planetary Geology Wind Tunnel to replicate dust and wind conditions on Mars.
If we can understand and sort of replicate what's going on, then we can, in a sense, understand how the Martian surface has been changing and continues to change as time goes on.
Oddly enough, their studies reveal that it's easier for winds to loft larger sand particles into the air than smaller dust particles.
This is because there's cohesional forces and static forces between the very small, fine dust grains. We imaged the rover deck and actually found that sand seemed to have bounced onto the solar panels, and we can see the skip marks across the surface. And this is interesting because we don't usually see sand typically reach that high.
Dust devils on Earth never have the punch to produce that kind of chaos here. Lucky for us. But what would happen to Earth if a giant Martian-style dust storm did overtake us?
If you had dust storms of Martian size on the Earth, you would find your city being enveloped in an orange-tan haze.
Air quality plunges as the storm churns. Dust blots out the sun, shutting down photosynthesis. No plants, no food. Temperatures would plummet. 65 million years ago, an asteroid may have struck the Earth, creating these same conditions, wiping out the dinosaurs.
It's not going to happen on the Earth, though, because there's going to be rainfall and moisture condensing on the dust grains and so forth and dropping them out of the atmosphere. So it's very hard for something like that to spread in the climate conditions that we have on Earth.
Forecasting Martian weather may someday be just as important as forecasting the weather on Earth. If we ever want to send a manned mission there,
the word environment no longer really applies just to the meadow next door and the little stream down at the end of town. It's the whole inner solar system. I mean, that's really our environment now.
The sun's energy bathes all the planets. On Earth, it creates hurricanes. On Mars, planet-wide dust storms. But with almost no solar energy, distant Neptune produces violent and powerful winds. Where do they come from? And just how bad are they? If Neptune's winds were to travel to Earth, these alien storms would literally blow us away. The orbit of Neptune lies 3 billion miles from the Sun, at the outer edge of the solar system. There's a lot we don't know about this big blue planet. Neptune's jet stream winds blast as fast as 1,500 miles an hour in its upper atmosphere. But how? The sun controls the weather on Earth and Mars, but it barely reaches out here. No sunlight means freezing temperatures, an average of minus 392 degrees Fahrenheit. So if there's no sun and no heat, where do these incredible winds come from?
One of the interesting puzzles is that as you go further out in the solar system, you get further from the sun, the winds don't go down. You still get very strong winds.
The energy for Neptune's winds must come from somewhere, and scientists are working to figure it out.
Neptune's energy is certainly not going to be powered by solar radiation. In fact, the energy we detect coming out from the planet in the infrared as heat is 2.5 times the energy coming in from the sun.
So the planet is creating its own heat, not from its core, which is made of rock and ice, but wrapped around this icy center is a mantle of ammonia, methane, and water, all being squeezed by enormous pressure and generating tons of heat. So while Neptune is frigid on the outside, on the inside it's giving off a lot of heat. This heat may help generate Neptune's winds, but they're still too strong to come from the mantle alone. Something else is pushing them faster and faster. Earth has a hot core too, and it's a lot closer to the sun. So why don't we have winds like Neptune? For one thing, our oceans store and release energy, and that helps generate our weather.
It adds energy in places, takes it out in others, in a very complicated system.
This complicated system produces a lot of wind. And just where are Earth's fastest winds found? Surprisingly, not over the ocean. They blow instead over the top of a fairly modestly sized mountain. New Hampshire's Mount Washington.
The highest winds ever observed by human beings were right here on Mount Washington at 231 miles an hour on April 12th in 1934.
Mount Washington Observatory, a private non-profit scientific institution, is responsible for tracking the weather and climate atop the 6,288-foot tall mountain. This remote weather station, accessible only by snow tractor in the winter, has kept daily records for the last 76 years.
It's definitely one of the most extreme locations on the planet. We regularly see in the wintertime winds exceeding 100 miles per hour every few days.
Nowhere near as ferocious as Neptune, yet still pretty strong. But why does this mountain, 1/5 the size of Everest, produce such fierce gusts?
We're at a place where we have winds converging from various directions, coming from the Ohio River Valley, coming down from the St. Lawrence River Valley, coming up the eastern seaboard, all converging here in this area on top of Mount Washington.
The elevation change from the valley floor to the summit of Mount Washington is very significant for any mountain range. It's over 4,000 feet, so air is forced to go over the mountaintop and forced to squeeze in there, and is accelerated as it's squeezed over the mountaintop.
And they measure it every hour, on the hour, 24 hours a day, 7 days a week.
It's blowing over 100 out here right now. Ice is forming on the instruments more quickly. It's time to go up and de-ice the instruments, even though it's blowing over 100. We got to do it every hour now.
Ironically, Earth's uneven surface, which channels winds into powerful gusts on Mount Washington, ultimately knocks them down over time. And this is the big difference between weather on Earth and weather on Neptune. Earth has mountains that slow winds down. Neptune is as smooth as a cue ball.
It's not so much a question of you're driving them stronger, because you're not. It's just that there's nothing to slow them down.
Simply put, once Neptune's winds get blowing, there's nothing to get in their way. So what would an average Neptune wind speed of 850 miles an hour do to us here on Earth?
We have parking level winds in the Earth sometimes above 100 miles an hour. We consider that pretty dangerous. So if we sat with 900 mile an hour winds from Neptune on the Earth, we would probably start wiping out everything on the surface and scraping everything off.
Giant Neptune takes wind and transforms it into something extreme and almost unrecognizable. But orbiting just beyond the rings of Saturn is a small moon that does the same thing to rain. This is Titan, where an everyday rain shower would turn Earth into an explosive fireball. It's a cloudy day, and a gentle rainstorm starts. Here on Earth, you'd grab your umbrella and consider it a minor inconvenience. But this isn't Earth, and it's no ordinary rain. You're on Titan, a small moon of Saturn. And in this chemical downpour, you'd need more than an umbrella to protect you. The rules of Earth weather definitely don't apply here. But Earth and Titan are alike in a lot of ways. On Earth, we have a solid surface, a protective atmosphere, and plenty of water. All these things make life on our planet possible. There's really nowhere else quite like Earth anywhere in the solar system. But Titan comes close. Like Earth, it has a solid surface. And that's not all.
Titan has an atmosphere that's, in general, very similar to Earth's. In some ways, it's mainly nitrogen like Earth's atmosphere. It's rich with organic material, also like Earth's atmosphere.
But similar isn't the same. Like water on Earth. So how do we know that this methane also falls from Titan's sky? That answer is shrouded in mystery. Literally.
Titan is completely covered in a thick haze of smog particles, like a very, very bad day in Los Angeles.
Despite the haze, the Cassini probe once again revealed the answer.
We can see the upper clouds, and we can see evidence for rainfall because the clouds drop very precipitously. We hypothesize that we're seeing the effects of rainfall.
Methane rainfall.
We think that Titan has methane monsoons, so we think that sometimes Titan has a lot of rain that is able to carve rivers and leave large fluvial deposits on the surface.
Cassini's radar imaging also revealed large methane seas on Titan's surface.
If you have liquid methane on the surface, in a lake for example, that methane can evaporate off and become methane gas in the atmosphere. So you have kind of a cycling of methane between liquid phase and gaseous phase and between the surface and the atmosphere that's very similar to the water cycle that occurs on the Earth.
But methane is a flammable gas. So why isn't Titan on fire?
For any combustion, you need two things. You need both a fuel, which methane is, but you also need oxygen. And on Titan, you lack the oxygen. So the whole thing is basically a big fuel canister, but there's no oxygen with which to burn it, and so it's all very stable.
If it were cold enough here on Earth to produce methane rain, the oxygen in our atmosphere would create a worldwide firestorm. Luckily for us, that can't happen. Titan's methane cycle makes it both alien and familiar to us.
To me, Titan is very exciting because all the materials are so different, and yet these processes produce very similar landscapes to what we see on Earth.
Titan proves that where alien weather is concerned, looks can be deceiving. On Jupiter, it's all about size. Drop the great red spot onto our world, and it makes even our worst hurricanes look like a breeze. This is the biggest and oldest storm in the solar system, and Jupiter's most famous feature. It even has its own name, the Great Red Spot.
It's about 2 or 3 times the size of the Earth, which makes it the mother of all storms.
We've known about the Great Red Spot in Jupiter's southern hemisphere for more than 300 years.
When Galileo invented the telescope, within a few tens of years, people had seen the Great Red Spot, and it's still there.
Familiar yet mysterious. Nobody knows how the Great Red Spot formed. But scientists are finally probing below Jupiter's cloud tops to uncover more about this enormous alien storm. The storm is powerful. With wind speeds of 300 miles per hour, it rises miles above the surrounding clouds. On Earth, we have storms that seem similar, though smaller and milder. Hurricanes, also known as cyclones or typhoons, depending on where they form. They're our most destructive weather systems. But is there more than just a passing resemblance between Earth's cyclones and Jupiter's red spot?
When you look at the Earth from space at a hurricane, it's this big swirling pattern. It's round, it rotates. Jupiter's big storms look big and round and cloudy and they rotate, but there the similarity ends.
In a hurricane, there is an internal core, which is called the eye of the tropical cyclone, and that's a region of very calm winds and no clouds, and usually has a size of about 10-20 kilometers in diameter. And then away from the eye, there is the eye wall. Those are really cloudy regions with a lot of rain. And as you move outward, there is a whole region of about a couple of 100 kilometers with very, very strong winds and very strong rain.
Hurricanes draw power from heat in our oceans. But Jupiter has no oceans. And the sun isn't close enough to power a storm as big as the Great Red Spot. So where does it get its strength? Part of the answer is Jupiter's size. It's the largest planet in the solar system, almost as big as all the other planets combined. This mass generates a very strong gravitational pull, which in turn creates interior heat that rises to the surface. Another piece of the puzzle may be Jupiter's hypersonic rotation. Despite being much larger than Earth, Jupiter's day lasts only 10 hours. In other words, it spins incredibly fast. Could energy from this dizzying spin feed the Great Red Spot?
The weather is really dominated by this fast spin. There's shearing between different latitudes, and that shearing, plus a lot of heat that comes up from the interior of this very massive object, 290 times the mass of the Earth, leads to very violent storms.
Both Jupiter's and Earth's storms spin around in a familiar spiral shape. On Earth, it's because of an effect called the Coriolis force.
I'm sitting at the North Pole, and I want to throw a ball down to a friend who's in Los Angeles. And so if I threw the ball in that direction, the Earth rotates, and the ball will end up in the middle of the Pacific rather than in Los Angeles. So it's like if the trajectory was deflected to its right. And that's what we call the Coriolis force.
This force spins storms clockwise in our southern hemisphere. But there is a stark difference between Earth and Jupiter. The Great Red Spot is in Jupiter's southern hemisphere, and yet it spins counterclockwise. This is because of some other powerful winds.
It's bounded by jets, which are moving in opposite directions. And so like a cog between two conveyor belts, they're just feeding energy and momentum into the system.
Jupiter's complex jet streams spin the storm into organized chaos. But the greatest difference between Jupiter's red spot and our storms may be Earth's solid surface. Once a hurricane hits land, it comes apart pretty fast.
Where they come over land or over mountains, their behavior is very different from where they form over the oceans and over warm oceans in particular, where we get hurricanes. And on Jupiter, there's obviously no solid surface.
With no land mass to stop it, the Great Red Spot just keeps on spinning and spinning and spinning. Scientists hope to learn more about our weather by continuing to study the storm.
On Earth, there's a limit to how far ahead you can predict the weather. On Jupiter, we can forecast where the red spot is going to be months in advance. It's practical value to understand what makes weather on Earth so unpredictable, and aspects of the weather on Jupiter are much more predictable.
Unpredictable or not, Earth's weather never gets as violent as on Jupiter. That's lucky for us, because if we shrank the Great Red Spot down to fit on Earth, we'd be in for disaster.
On the Earth, we go up to Category 5 hurricanes, nothing but Category 10 hurricane here. Not much would be left.
Alien storms are vastly different everywhere you go in our solar system. Even our next-door neighbor, Venus. They say we're sister planets. Lucky the resemblance doesn't include weather. Otherwise, we'd get seriously burned. Venus may be our nearest neighbor, but somehow its weather is radically different from ours. The second planet from the Sun is a cross between a toxic waste dump and Death Valley, but even worse.
So it's almost a planetary definition of hell.
The temperature is 900 degrees Fahrenheit. The pressure on the surface is the same as half a mile below the Earth's ocean. And if that's not enough, the upper atmosphere of Venus is choked with sulfuric acid clouds and winds clocked at 250 miles an hour.
To get a comparison for Venus, the best thing to do is climb inside of your oven and crank it up. And then in terms of pressure, you're talking about deep sea diving. It's like nothing. There's nothing comparable on the Earth. It's just a very, very extreme object.
On Venus, there's just no escaping the heat.
If you built up a hot spot on Venus, the massive atmosphere would just carry that heat away and spread it around.
But Venus shines so brightly in the night sky because its thick clouds reflect almost all the sunlight it receives. In fact, some early scientists assumed Venus would have moderate Earth-like temperatures.
When we went by Venus in 1962 with a spacecraft, we thought we would find a surface at 90 degrees Fahrenheit, sort of like Miami, Florida.
We were dead wrong. Something else must be at work on Venus. But what? So why doesn't Venus cool off the same way Earth does?
On the Earth, for example, we have sunlight coming in, hitting the surface of the Earth. Earth warms up a little bit, but the oxygen and the nitrogen in the atmosphere don't impede the light, so when it gets released out in the infrared, it goes right through the atmosphere and leaves and goes into space.
But on Venus, the atmosphere is 97% carbon dioxide, giving a whole new meaning to the greenhouse effect.
It becomes very, very hard for the surface to get its energy out.
So Venus really taught us a lesson, that if you have a blanketing gas, a greenhouse gas, it can warm up the atmosphere tremendously.
But why does Venus have so much more CO2 in its atmosphere than Earth? The two have much in common. They're even called sister planets. They're almost the same size, have roughly the same amount of carbon, and billions of years ago, both had lots of water. But eons ago, their paths mysteriously diverged. On Earth, water fostered life.
The Earth has most of its carbon in life forms, in the trees and the animals. But if you took all that carbon that's in the near-surface rocks and burned it up or released it, you would then create an atmosphere very much like Venus.
Venus's close proximity to the sun made it too hot to sustain liquid water. Instead, its water evaporated into the atmosphere, trapping the heat deposited by the sun and creating a runaway greenhouse effect. Once in the atmosphere, the water molecules were exposed to solar ultraviolet rays that broke the molecules apart.
It really wasn't recognized by the scientific community how important the greenhouse effect was prior to going by Venus and seeing this amazing place where it was 900 degrees Fahrenheit, not 90.
It took several doomed missions to Venus to figure it out. Starting in the 1960s, both the United States and the Soviet Union sent unmanned probes past the planet and down to its surface. It didn't take long before Venus crushed and burned them. Then, in 1981, the Soviet lander Venera 13 set a record for survival on the surface of Venus. 2 hours and 7 minutes. It was able to take pictures and samples of the surface before being overcome by the heat.
You're sitting there with this 900 degrees Fahrenheit heat all around you. It's going to get in there and bake you after a while.
Scientists one day hope to send a probe to Venus that can survive its hellish environment, to help us confirm our theory of how this planet went astray. Because if circumstances were just a little different, our sister planet might just be our twin. Remove our atmospheric shield, and you're on the road to hell.
As soon as you're heated up to something like 400 degrees or so, you probably start getting some smoldering smoke, and way before it gets to 900 degrees, the Earth would burst into flames because of all the oxygen around.
Once the oceans boiled away, the carbon locked in rocks on the ocean floor would cook, and over millions of years re-enter the atmosphere.
Probably if you came back to the Earth system after this happened, you'd find a planet looking much like Venus.
We're a long ways away from such a drastic change, but it's sobering to look at Earth's sister planet when the sister planet went on a very different track than we did.
So cosmic forces turned Venus into a planetary barbecue. But on this violent, stormy world, time and the elements have produced some of the strongest thunderstorms ever measured. Welcome to Saturn. Lightning cuts the sky. This violent weather system grows bigger than the entire United States as it pummels the atmosphere with the most powerful lightning ever seen. Except this lightning can't be seen, because these bolts are electrifying the skies over Saturn. Despite the raw power of Saturn's lightning, scientists have been unable to see it, partly because Saturn's rings are too bright.
The rings are so bright, if you were on the night side of Saturn, it would be considerably brighter than the Earth under a full moon.
But Saturn also hides its lightning within thick, choking clouds of ammonia.
It's probably 100 kilometers down that the lightning is happening, and that complicates seeing the lightning flashes.
But the lightning is there, and scientists know it because they've heard it. Radio wave detectors on the Cassini orbiter have recorded the sound of Saturn's lightning.
We can hear the static of lightning just as you could with an AM radio going down the highway on Earth.
And this static reveals the power of the lightning that we can't see.
You can measure the energy in those radio waves and compare it with the energy that your radio picks up when there's a thunderstorm around on Earth. And the Saturn ones are big. They're more powerful, maybe 100 times.
And Earth's lightning can help scientists understand how storms work on Saturn. Within Earth's storm clouds, just like in Saturn's, updrafts drive moisture higher, causing ice to form. These ice crystals rub against each other, take on a positive charge, and become attracted to negatively charged water droplets lower in the cloud. This sets the stage for a potentially powerful discharge of energy.
Once you get that charge separation that builds up so intensely that some theorize that it can be as strong as 100 million volts, that the cloud then must release that energy.
On Saturn, the same thing happens on a much larger scale. In fact, the lightning is 100 times stronger than Earth's. That's a staggering 10 billion volts of electricity. Thunderstorms in Saturn's southern hemisphere span thousands of miles and can last as long as a month. But scientists aren't sure what makes Saturn's storms bigger and longer lasting. It could be Saturn's supersaturated atmosphere.
Probably the fact that there's more water in the atmosphere, pound for pound, on Saturn makes the storms bigger.
More water droplets means more friction, which means bigger lightning bolts. But energy emerging from the planet may also contribute to the power in Saturn's thunderstorms.
It turns out that where Lightning Alley is on Saturn is a place where the winds are flowing the slowest. If you go deep down in the atmosphere, you'll see the same winds as you do up high. It's a place where the energy being released deep down below can make it on up to the upper atmosphere without being sheared apart, and allows storm systems to be organized.
Earth's atmosphere isn't built that way. So, as violent as our storms get, they're nothing compared to the systems on Saturn. Even a run-of-the-mill mega thunderstorm on Saturn would devastate us here.
A Saturn-sized thunderstorm on the Earth would mean a thunderstorm that grows to cover all of North America and presumably has very strong winds and rain. This is something that's unprecedented on the Earth.
Saturn's hyper-violent thunderstorms are proof that our planetary neighbors have weather far more ferocious than ours. But the laws of physics that create Saturn's storms are the same laws that create our own weather. Massive dust storms, unrelenting winds, killer lightning, powerful hurricanes, and searing heat.
The goal is to delve into the unknown world beneath the surface for signs of past habitability. A diamond-tipped drill on a robotic arm does the delving. Samples of rock and soil obtained in this way are analyzed on the spot. Scientists are looking for organic compounds that might have permitted life on Mars.
Curiosity and the entry, descent, and landing system are revolutionary. It's a real laboratory, and it's a laboratory on wheels. And what that means is we can take it around to different places and study the rocks, and then from that reconstruct different environments that existed in the early history of Mars.
However, Curiosity has been afflicted with a host of problems, from computer glitches to solar interference with communications.
We may have lost the rover forever.
But Curiosity surmounted such crises and resumed its quest. It soon discovered, beneath the famously red Martian terrain, an unexpected world of gray. This finding greatly increased the chance that life has indeed been possible on Mars. Curiosity is continuing its rambles on Mars. This program tracks its adventures over the course of 1 year. Curiosity first entered the Martian atmosphere in August 2012. Executing thousands of commands, it approaches its landing area. One mistake could send it crashing into the surface.
We are in powered flight.
Rover is guided to its target landing area by radar. As it descends, it must skim over a 5,000-meter high mountain range.
Sky crane has started. Safe on Mars.
Curiosity has landed safely on Mars. 2 minutes later,
Images. Got thumbnails. It's the real. It's the real. We are wheels down on Mars.
the first image received was the brilliant globe of the sun, shining a benediction on Curiosity's mission. Then, far off in the distance, rose the 5,000-meter peak of Mount Sharp.
There was no way to know in advance that the rover would be oriented so that you could see that. But it was really great to see the mountain that we had observed from orbit and realize that we could make that target someday.
The rover had landed in a giant crater near Mars's equator. Some scientists speculated that once there was a great body of water here. That made it the perfect place to search for conditions permitting life. Curiosity's adventures were about to begin. The day after the landing, Curiosity raises its head and looks about slowly. It has 2 pairs of navigation cameras. These cameras can cover a 360-degree panorama, taking 3D images of the surrounding terrain. 2 high-resolution cameras are also affixed to the mast for distant and wide shots. The procedure is to take multiple color images, then combine them so as to produce a detailed panorama. From the pebbles in the foreground to the formation several kilometers in the distance, all is revealed in vivid detail. Now that Curiosity's imaging systems have been checked out, it's time to confirm mobility. Mission Control commands the rover to start moving. First off, it goes 4.5 meters directly ahead. Then it executes a 120-degree turn. Next, it will move backward 2.4 meters. Even these baby steps put Mission Control under agonizing pressure. At this time, Mars is about 260 million kilometers from Earth. For each command to reach Curiosity, it takes over 15 minutes. Then for the result to make its way back to Earth, it takes another 15 minutes. In the unlikely event that some mistake is made in a command, it could be fatal to the mission. In the present case, they've waited 3 hours since sending the commands. An image arrives from Curiosity. The rover's tracks on the Martian surface, precisely as commanded. This is a promising start. Curiosity landed at the red dot, in the plains at the base of Mount Sharp. The rover's first destination lies 500 meters to the east, at the seams of 3 rock plates, comprised of different materials from different eras.
We recognized that we were going to be able to study a kind of a rock that we saw from orbit that had this signature of very high thermal inertia. And we thought maybe the water was involved in precipitating minerals that filled in the pore space. That's why we decided to go, because we thought maybe the property of thermal inertia has something to do with water.
Curiosity fixes its navigation cameras on its destination. Mars, the red planet, glows in the night sky. It is Earth's neighbor. Could it harbor life? People have long pondered that question. One of them, in the late 19th century, was the American astronomer Percival Lowell. His observations of the planet over 15 years led him to conclude that there were traces of numerous canal-like structures on the Martian surface. Lowell concluded that, unquestionably, Mars, too, boasted an advanced civilization. But in the 20th century, Mars missions sent back images showing no trace of actual canals. What the images did show, however, looked like traces of the flow of water. Even if there was no intelligent life, might there not be at least some primitive organisms? Speculation mounted. What are the requirements for life to exist? On Earth, there are a minimum of 3. First, liquid water. Among its many and varied functions, it conveys nourishment to every part of our bodies. Second, an energy source. This is vital for such basic aspects of life as growth and reproduction. Third, organic compounds. These are the raw materials out of which life takes shape. In 1997, however, the Pathfinder probe made a stunning discovery that seemed to dash hopes of life on Mars. With expertise in both geology and biology, Jack Farmer has been a valued contributor to every major Mars mission from Pathfinder onwards.
I suggested that we go to the outflow channel called Aeris Vallis, which was draining from this terrain of potentially lots of different kinds of habitable environments, carrying water from the subsurface up, draining out and depositing right where we landed.
However, when the surfaces of the rocks and ground were inspected directly, scientists were disappointed. The rust-colored Martian terrain looked extremely inhospitable. Jack Farmer calls such a highly oxidized surface a real killer for life.
Oxidation reactions are always going on the surface of Mars, and this kind of surface skin of basaltic materials like this gets turned to something like this. So Mars is red, for a good reason, I guess.
This is how it happens. Cosmic rays pass right through the thin Martian atmosphere, directly striking the planet's surface. That produces a large number of active oxygen atoms. They bind with iron in the rock, producing the characteristic rust color of oxidation. Active oxygen has a powerful impact on organic compounds, the very building blocks of life. It splits them off, disintegrating the compounds.
If they're there, they're very shortly oxidized and turned into CO2.
The bleak, reddish surface of Mars. It proclaims the fierce oxidation of a sterile world. Hopes faded for even a historically habitable Mars. But now, Jack Farmer and other scientists are following a promising new lead. They're looking inside rock formations, where cosmic rays cannot reach.
If you go in the subsurface, different story. If you can get down deep enough where there could be water present, then you've got a whole different ballgame, and I think you could open the door for life down there.
Could there be, hidden beneath the arid terrain of Mars, an entirely different environment, one hospitable to life? Answering that grand question is Curiosity's mission. Pre-op checklist completed. Curiosity is good to go. As if to pray for an indefinite continuation of its mission, Curiosity etches the infinity symbol in the Martian soil. August 27th, about 3 weeks since the landing. Curiosity is ready to venture forth. One of its early finds is a strangely shaped rock. This pyramid-shaped rock, about 30 centimeters on an edge. It makes a good test subject for some new equipment. The ChemCam, a laser spectrometer and imager. As the laser beam bores in, the ChemCam analyzes light from the vaporized rock to determine composition. The pyramid rock is found to be a volcanic rock, basalt, rich in metals like iron and magnesium. Its remarkable angular shape is thought to be the result of wind erosion. Curiosity continues its trek through fantastically bleak scenery. As it travels, its cameras record some incredible sights. Like this partial solar eclipse. Mars has 2 moons. One of them, Phobos, has passed overhead, partially obscuring the sun. This is the first time a Martian solar eclipse has been captured so distinctly. Curiosity soldiers on, sending back image after image, at a pace of more than 200 a day. One image in particular catches the attention of mission scientists back on Earth. It was taken just 100 meters from the landing site. It shows a large number of pebbles strewn about at the base of some uplifted bedrock. Very similar terrain can be seen on Earth. Dry riverbeds. These pebbles were rounded by friction as the current ran its course. Now the eroded, dried-up channel is littered with them. Compare them side by side. Similar indeed. This is incontrovertible proof that water used to flow in this region. The first of those 3 requirements for life has already been satisfied. Experts can use the size and disposition of the rocks to guess how that river flowed in ages past on Mars. The river would have been about knee-deep, and it flowed at about the speed of a human walking.
So when we saw the ancient streambed gravel, you think of flowing water. And one of the things that you want to do is go with the flow. Follow that river. See if you can see where it takes you. Because on Earth, when you follow a river, it either leads to an ocean or it leads to a lake.
So Curiosity goes with the flow, eastward. What sort of scenery awaits it? Before we follow Curiosity any further, let's acquaint ourselves with the hard work done by the mission control staff. This is mission control at JPL. Work here continues regardless of day or night. The main reason for that is the time difference between Earth and Mars. Mars takes longer to rotate on its axis than Earth does, so its day is 40 minutes longer, which means the time difference between Earth and Mars after 3 days is 2 hours. After 6 days, it's 4 hours. The gap widens. Curiosity can be activated only during the Martian daytime, but there are times when that might be in the middle of the night on Earth. One of Curiosity's planners and drivers, John Wright, is starting work at 9 p.m. It's the beginning of a hard day's night. His first step is to review the log of the previous day's itinerary. Next, he analyzes closely the 3D images produced by Curiosity and decides which route to take next.
So with 3D, I can see there's a small mound here. There's a large mound right here. So if I'm going to be driving forward, I'm going to go over that mound and then down a fairly steep hill on the other side. So I might say, maybe that's a little steeper than I would like to drive. But let's try to analyze some other areas. So we might look at other areas. I had to work sometimes all night, sometimes all day, sometimes halfway from the middle of the day to the middle of the night, all different kinds of odd shifts.
Okay, this side.
Well, sometimes I would go, since my wife would be asleep when I would go home, I'd go someplace to a late night restaurant and have dinner. Or breakfast or whatever it was, because it was just easier to do that. But then, after all that work, to find something really interesting and really amazing, it does make it worthwhile. I mean, that's why we're here, is just to do exactly that.
About 2 months after the landing. Just short of its next science destination, Curiosity encounters a new formation. The rock nest drift of windblown sand and dust. Curiosity takes this opportunity to test for organic compounds, which are vital to life and are a key target of the mission. The SAM laboratory suite is highly efficient at detecting organic compounds. Paul Mahaffey is NASA's principal investigator for these analyses on the Curiosity mission.
So this is a full-size model of SAM on Mars. This is the electronics box. This is the mass spectrometer. This is a gas chromatograph. And our third instrument, the tunable laser spectrometer, is down here.
All these analytical instruments are packed into a laboratory suite about the size of a microwave oven. And in fact, samples introduced into it are first heated at high temperatures. The gases given off by this process are then analyzed minutely by the mass spectrometer to determine their constituents. When the sand and dust of the rock nest site were analyzed, the results were stunning. Trace amounts of chloromethane, an organic compound, were detected. At last, a key ingredient for life on Mars had been discovered. The scientific community was all abuzz. However, at a hastily called news conference, the project's leaders were cautious in their claims.
SAM has no definitive detection to report of organic compounds with these first set of experiments.
The SAM laboratory suite had been assembled in a terrestrial clean room. Despite all the team's precautions, could impurities have entered it? Possibly it was those impurities that had been detected.
As far as the first analysis of the rock nest sample is concerned, we certainly couldn't definitively rule out that most or even all of that carbon might be from Earth.
But this uncertainty only intensified the hopes placed on Curiosity. Soon the rover would arrive at its primary science destination, where it would be expected to find definitive proof. December 7th, 2012. After about 4 Earth months, the rover has finally reached its primary destination for exploration. A new type of terrain has come into view. To the southeast, a bulge of bedrock. To the northeast, a low-lying area. Curiosity heads into the low-lying area. What will it find? A basin stretching as far as the eye can see. The bedrock is cracked but flat, like an interminable expanse of stepping stones in some giant garden.
The character of the rock is much different. We have mud cracks and things of that nature that suggest perhaps this was a lake that actually, a shallow lake that would dry out occasionally and produce cracking.
This dried out lake bed has been named Yellowknife Bay. That ancient river Curiosity discovered right after setting out had once flowed down here and created a magnificent lake. Next, Curiosity will put a drill to work to obtain a historic first sample from underneath the red ground of Mars. The rover descends carefully into the bay itself. It will spend the next 40 days exploring the bay's every nook and cranny.
And then we drove up to another particular part of the outcrop where you could go up it centimeter by centimeter by centimeter and do a detailed study. And then we did that. And then ultimately, that helped us pick the place where we wanted to drill.
The basin was vast. Where to drill was indeed a matter requiring thought and planning. Curiosity finally finds a target that looks perfect for drilling. A flat and stable rock bed. It is given the name John Klein. February 8th, 2013. Whether it's been day or night on Earth, John Wright has continued his skillful maneuvering of the Curiosity rover, and he's been formulating complicated commands to operate the drill. He runs simulation after simulation. Accurately excavating the target spot requires extremely delicate manipulation of Curiosity's robotic arm.
So when you put the arm out, it just sags down because of the weight, and it can sag up to 7 or 8 centimeters below where you command it to. When you say go to 10 centimeters, it says, well, in this configuration I might have 5 centimeters of droop, so I'll command it to 15 and expect it to droop down to 10. That, making sure all that worked right, was the stressful part.
After spending more than 5 hours assembling the command sequences, Wright sends them to Curiosity. The next day brings images of the results.
That's an image here of our first hole on Mars. Big success. Yep. Woo! Yeah.
This was the first time in history that human beings had drilled a hole into another planet. Note the color. Beneath the red surface, gray rock tinged with green.
I think when we first saw the color of the rock that was being exposed as a result of drilling was one of the most exciting moments of the entire mission to me. It was right up there with landing itself, because when you see this gray color and you know the chemistry in advance, when the iron is more in the reduced state, you can get a grayer color, which is the color of, say, for example, iron metal is gray because all the iron is reduced in that state.
The sample extracted from the rock is placed into SAM, the specialized onboard laboratory. There it's analyzed for the presence of organic compounds. But just when Mission Control thought the data was coming in fine,
it'll be hard to see above the noise floor in the FFTs given how weak the low gain signal is. Yeah.
an unforeseen circumstance. The main computer controlling all of Curiosity's equipment has developed a serious glitch. The data stream has suddenly been suspended. The mission specialists concentrate as a group on troubleshooting the problem. They pinpoint the culprit, the main computer's flash memory, dedicated to preserving Curiosity's analytical data. What's worse, further analysis reveals that after several hours, if nothing is done, Curiosity will cease receiving instructions from Earth.
This computer would stop talking to Earth. We wouldn't be able to send commands to it. It would stop. It would do no more help for us, and the computer would forever be locked in this perpetual loop, never communicating to us again. We may have lost the rover forever.
If communication with Curiosity becomes impossible, the rover will be stranded on Mars as a pile of very expensive junk. Is there no way to prevent that worst-case scenario? Their discussions produce, in the end, an all-or-nothing solution.
We've got to do something. We've got to kill this computer. It's not going to kill itself. This computer is going crazy. We have to take it offline.
So the troublesome primary or A-side computer will be taken offline, and they'll switch to the B-side backup. The problem is, once they've shut down the main computer, will the backup boot up properly or not? There are absolutely no guarantees. But there are also no alternatives. So the main computer is shut down, and the backup is switched on. The result?
But we waited and waited. When the minute came, 5, 4, 3, 2, 1. Nothing. We saw no signal. We all look at each other. Did we do the math wrong? Let's go check the math. No, we didn't do the math wrong. Now we're very nervous that maybe we messed this whole process up and that we missed the command or did something wrong.
Project staff all resigned themselves to the worst.
We confirm we are watching the FFT display. We don't see any signal coming.
Happy. 3 minutes later, there is a signal. Later on, we realized that the new computer watch hadn't been updated. Okay, so that makes sense, but we didn't realize it was off by 3 minutes. But we were very relieved. Once we saw that signal, knew we were in good shape.
Curiosity had surmounted the crisis and obtained some hard-won samples of gray Martian rock. The precious analytical data were successfully streamed to Earth. Washington, D.C. NASA held a press conference at its national headquarters. Project leaders reported on Curiosity's latest achievements and on the possibility of past life on Mars.
Yellowknife Bay. This was an ancient environment with the right elements, minerals indicating a near-neutral environment, and slightly salty liquid water. All the prerequisites to support life. A habitable environment.
The first step was to introduce the gray powder obtained by the drill into the Chemin instrument, a component analyzer. Analysis confirmed that the deeper the sample, the weaker the oxidation of the rock. This finding meant that the second requirement for life on Mars, an energy source, had now been satisfied.
It's a battery. And basically, these minerals that Dave and Paul were telling you about, they're effectively like batteries. Some of them are negatively charged, and they have various oxidation states.
The difference in oxidation states meant that electrons could flow from areas of weaker oxidation to areas of stronger oxidation. Even the minute flow of these electrons constitutes energy and could promote an environment conducive to the nurture of microorganisms. Jack Farmer points out that similar environments occur on Earth. This is a sample from inside a cave, in a place that sunlight does not reach. But check it out under a microscope. And masses of a stringy microorganism are still living in the sample.
It always participates in the oxidation of reduced iron in systems like that. So it's mining this reduced iron spring for its energy. It's not using sunlight, because there's no sunlight there. It's using only chemistry, redox chemistry.
Curiosity had proved that even under the surface of Mars, an energy source existed sufficient to satisfy one of the three requirements for life.
We're no longer just looking at a red, rusty Mars. We have evidence that there's something going on in the shallow subsurface. You don't have to go very far, right? A few centimeters, and you're into a totally different world.
And made a model.
Next, there was the question of whether the rock samples contained the final requirement for life on Mars: organic compounds. Concerned about potential contamination from Earth, the Mars team had given Curiosity's onboard analytical equipment a blank run to establish baselines. Only then did they introduce the sample for analysis. The result? another finding of chloromethane. It was nearly 5 times the amount detected during the blank run. Clearly, most of what was detected in the sample had not been brought along inadvertently from Earth. But Paul Mahaffey, in charge of the analysis, knew they could not jump to any conclusions. Chloromethane alone is insufficient to guarantee the presence of life.
Chloromethane compounds are the simplest class of organic compounds that you can find. It's very much on the simple end of the types of complexity that we're looking for.
Curiosity will have to locate more complex organics. Undaunted, the rover heads off to its next science objective. However, it will first undergo an ordeal even more harrowing than the last. Up to this point in the mission, Curiosity has faithfully executed every command sent to it. But ever since that glitch developed with the main computer, Curiosity has been run by its B-side or backup computer. If this backup computer develops any serious trouble, that really will be the end for this groundbreaking mission.
We also need to figure out what happened to the A side and figure out whether or not we can restore it so that we can use it again if we need to in the future.
A new problem is looming at this crucial moment: solar interference with the mission's communication signals. With an orbital period almost double Earth's, Mars finds itself, once every 2 years, on the opposite side of the Sun from Earth. In other words, the Sun is interposed between Earth and Mars, blocking a direct line of communication. The Sun emits an exceptional amount of charged particles. They stream off the Sun as the solar wind. When signals are sent from Mars to Earth, the solar wind can interfere, letting only some of the data arrive. What's even scarier is that commands sent to Curiosity could be corrupted en route, delivering the wrong instructions. So for about a month, communications with Curiosity will be deliberately shut down. Project engineers are desperate to get the main computer back online before Curiosity goes into standby mode.
So, I need to we can set the pointing angles to right and down.
The computer repair work continues day and night.
And we did it all in about 3.5 weeks, and just in time for conjunction. So it was a very exciting month of March.
Succeeding in their repairs before the conjunction of the Earth, Sun, and Mars, the team is able to safely ride out this period of suspended communications. After 1 month, Curiosity is back online, communicating with Earth. Engineers immediately send commands for a second drilling experiment. And again, gray Mars appears. But analysis once again finds only chloromethane, no complex organics. Does this mean there are in fact no complex organics at all on Mars? At this point, one scientist offered a new proposition concerning the possibility of past life on Mars. Chris McKay is a co-investigator on the Curiosity mission. McKay has an explanation for why complex organic compounds have not been found on Mars. A clue, he says, is provided by the large amount of perchlorate found on Mars. What does he mean? McKay demonstrates with an informal experiment.
Okay, a little perchlorate. And a little sugar. Sugar represents the organics on Mars that we would like to detect.
Sugar, the well-known complex organic compound resulting from photosynthesis by the sugarcane plant.
As I heat it,
Sam detects organics in the same way, by heating the sample. McKay is mimicking the basic process. The sugar begins to melt.
Sugar's active.
That activates the perchlorate. A moment later,
Perchlorate to heat up. That's the perchlorate burning.
So the activated perchlorate destroys complex organic compounds like sugar. The reaction also produces chloromethane.
Right. Once you heat up the sample with organics, it's all going to get turned into chlorinated organic compounds like chloromethane. Even if there was a biosignature in the sample, say some cells, they would be destroyed by the perchlorate.
But that means that in a location with less perchlorate, there would be a better chance of finding complex organics. And McKay has a theory about just where to look: deeper underground.
That material certainly had organics when it was deposited. So something is bleaching the organics out. And that something must be perchlorate chemistry activated by radiation. So we have to go deeper.
Curiosity's drill can go 10 centimeters deep at most. But the side of a cliff might provide a way to get at exposed rock from deeper layers. A place like Mount Sharp, seen in that snapshot taken just after landing.
We go up Mount Sharp and we find a place where a landslide or an impact has removed material, and we can get down below the ground more than 5 meters with the rover. That would be wonderful.
Day 299 since the landing. Its investigation of Yellowknife Bay complete. Curiosity has a new destination. It's heading off to Mount Sharp. There, complex organic compounds, those building blocks of life, may yet await discovery.
Maybe we can find an environment where there's not so much perchlorate. Or maybe we can find an environment that just has lesser amounts of oxidants. That's what we're trying to do. We're trying to figure out how to unlock the code for the preservation of organics now.
As a geobiologist, Jack Farmer greatly looks forward to this next chapter of Curiosity's saga.
When you combine geology with the quest for life, it's a whole other ballgame, and that's really what's kept me interested. Being able to see through that story in the rocks, to ask the question, could life have survived here in the past? Could it still be there today in the subsurface?
It's only been 1 year so far, and Curiosity has already shown us a brand new gray Mars. Its next destination on Mars is a land whose colors and contours we still do not know. Curiosity is exploring new territory in the effort to determine whether or not Mars has ever been able to sustain life. That epic quest continues.